Hi there, I'm David Dye and I'm going to introduce you to this course on linear algebra. Later in the course, Dr. Sam Cooper will take you through the last module, and in his course on multivariate calculus I'll do a bit in return. But in this video I just want to take a moment to introduce the course and what we're trying to do here and to set the scene. The world is awash with huge amounts of data. Most of us living in cities generate huge amounts of data as we go about our lives, moving around, browsing our mobile phones, using transit networks and consuming energy. If we just think about energy alone for a moment, our society literally lights up our planet from space. We can see where the people and economic activity are from the light. Zooming into Europe and London here, you can see how some of the world's great cities network together. This takes a huge amount of energy. And if we're going to figure out how we're going to generate and use energy more sensibly in the future, we're going to have to understand the data we have about energy much better. If we don't want to damage our health with NOx and particulates, and if we want to combat global warming, we're probably going to have to strongly cut back or even eliminate burning hydrocarbons as the leading approach to powering our society. And we can. With wind, with nuclear, with solar, we can probably make huge strides towards reducing our need for fossil fuels. But we're going to need storage and batteries in order to have hybrid and battery electric vehicles. We're going to need to insulate our buildings much better and heat them much more efficiently. But where should we start? Where are the opportunities to have the biggest impact soonest? If we install this energy saving measure, how much will it cost and how much will it help? Should we recommend that everyone buy heat pumps, or should people first insulate their homes better? How much range do electric vehicles really need? How big should their batteries be? In improving the London Underground so that more people use it and less people drive, are there stations that are so close together that there's no need to stop at them most of the time? All of these questions we could answer better if we could analyse the energy and usage data we had better. If we had good models of data, then we could also make predictions. Practically speaking, we could build software that tells you how to take the fastest journey across your city and put it in an app, or which web pages you might want to see in response to a search query. And we don't necessarily need a physical model in order to make such predictions. Neural networks are very accurate in many applications at modelling data and making predictions. And the process by which we optimise those networks is called machine learning. Now it turns out that linear algebra, how to solve systems of equations like this, where the variables obey the rules of vectors, like these, and then taking those forward and recasting them as matrices, like these objects here, this is very important in machine learning and data science. And also, being able to do optimizations in machine learning and data science in turn depends on understanding how a thing we're trying to optimize changes in response to changes in the parameters that describe it, which is multivariable calculus. These sorts of symbols here. The problem is that machine learning and data science have their origins in computer science and mathematics. But more and more, we're wanting to use that maths by engineers and physical scientists and biologists and people working in medicine and social scientists and so on. But one of the problems is that most courses on data science and machine learning presuppose a level of familiarity with linear algebra and calculus that not everybody has. So our aim in this course and in this specialisation is to revisit the underpinnings in vectors and matrices and calculus that you may have touched on in school but which you might never have applied. Depending on how it was taught, it may not be at all obvious to you why that maths would even apply to the world of data. Usually high school maths is motivated, if it is at all, through physics, after all. So this might not be that obvious. To be clear, we're not really aiming to do a fundamentals course where we do everything very rigorously, as we would if we were trying to set up for a graduate school class in applied mathematics later. Nor are we aiming for the breadth of a linear algebra or a calculus course that would apply everywhere across science and engineering. We're just aiming to, very quickly and in a way strongly motivated by machine learning problems, give you enough underpinnings to get you going. And more than anything else, we want to develop your mathematical intuition. That is, we have computers to do all the mathematical operations for us now, in Python or MATLAB or R. And some of the most complex exercises at the end of these courses will ask you to write some very short little mini blocks of code in Python to develop and demonstrate and use the mathematical insight you've developed. But doing the operations and crunching through them with pen and paper, plugging the numbers and chugging your way to the answer, it's just not a very useful skill in the world anymore. So our focus is on the ideas, not on your endurance. So, linear algebra is defined to be the study of vectors, vector spaces, and mapping between vector spaces. It emerged from the study of systems of linear equations and the realization that these could be solved using matrices and vectors. So the first thing we'll do is look at vectors and the operations we can do with vectors. And then we'll move on to look at matrices, and then in the final module we'll put it all together with an application to Google's famous Pagerank algorithm for ranking web pages. So that's what this course, Linear Algebra, is all about, and how it relates to the other courses in this specialisation on multivariate calculus and machine learning. So welcome. In this video we're going to look a bit more at the types of problems we might want to solve and expose what linear algebra is and how it might help us to solve them. The first problem I might think of is one of price discovery. Say I go shopping on 2 occasions and I buy apples and bananas. And the first time I buy 2 apples and 3 bananas and they cost €8. And the second time I buy, say, 10 apples and 1 banana and the cost is €13. And the A's and the B's here are the price of a single apple and a single banana. And what I'm going to have to do is solve these what are called simultaneous equations in order to discover the price of individual apples and bananas. Now, in the general case of lots of different types of items and lots of shopping trips, then finding out the prices might be quite hard. It might be quite difficult to solve all of these equations by hand. So we might want a computer algorithm to do it for us in the general case. Now, this is an example of a linear algebra problem. I have some constant linear coefficients here, these numbers, 2, 10, 3, 1, that relate the input variables a and b to the output 8 and 13. And that is, if I think about a vector AB that describes the prices of apples and bananas, then this gets translated into a cost if I know how many of them I want to buy, and the cost happens to be 8 on the first trip and €13 on the second trip. And I can write this down as a matrix problem where the 2, 3 is my first trip and the 10, 1 is my second trip. And then these are then matrices, that's a matrix then, and these are vectors. And what we're going to do over the course of modules 1 to 3 is build up looking at these different types of mathematical objects and understanding what they are and how to work with them, these vectors and these matrices. And then we'll come back and figure out how to solve this problem in the general case. Another type of problem we might be interested in is fitting an equation to some data. In fact, with neural networks and machine learning, we want the computer in effect not only to fit the equation, but to figure out what equation to use. That's a highly inexact description, really, of what's going on, but it gives the right sort of flavour. But let's say we have some data like this histogram here. This looks like a population with an average and some variation here, some width. Another type of problem we might want to solve, as well as the apples and bananas problem, is how to find the optimum value of the parameters in the equation describing this line, the ones that fit the data in the histogram best. That might be really handy. Then using that equation, we'd have an easy portable description of the population we could carry around without needing all the original data, which would free us, for example, from privacy concerns. Now, we could plot how good the fit was in terms of the parameters. And that's what we'll look at in the next video. In this video, we've set up 2 problems in this first module on linear algebra. First, the problem of apples and bananas, of solving simultaneous equations. And secondly, the optimization problem of fitting some data with an equation with some fitting parameters. And these problems we'll go on to look at and motivate our work right through the course on linear algebra and its partner of multivariate calculus. So the first thing we need to do in this course on linear algebra is to get a handle on vectors, which will turn out to be really useful for us in solving those linear algebra problems. That is, the ones that are linear in their coefficients, such as most fitting parameters. We're going to first step back and look in some detail at the sorts of things we're trying to do with data and why those vectors you first learned about in high school are even relevant. And this will hopefully make all the work with vectors a lot more intuitive. Let's go back to that simpler problem from the last video, the histogram distribution of heights of people in the population. You know, there aren't many people above about 2 meters, say, and there aren't really very many people below 1.5 meters. Say we wanted to try fitting that distribution with an equation describing the variation of heights in the population. And let's say that equation has just two parameters, one describing the centre of the distribution here, and we'll call that mu, and one describing how wide it is, which we'll call sigma. So we could fit it with some curve that had two parameters, mu and sigma. And I would use an equation like this. I'd call it f of x, some function of x, where x is the height, is equal to 1 over sigma root 2 pi times the exponential of minus x minus mu squared divided by 2 sigma squared. So this equation only has two parameters, sigma here and mu, and it looks like this. And it has an area here of 1 because there's only 100% of people in the population as a whole. Now don't worry too much about the form of the equation. This one happens, this is called the normal or Gaussian distribution, and it's got a centre at mu and a width of sigma, and it's normalised so that its area is 1. Now, how do we go about fitting this distribution? That is, finding mu and sigma, or the best possible mu and sigma, that fits the data as well as is possible. Imagine that we had guessed that the width was wider than it really is, but keeping the area at 1. So if we guessed that it was a fatter and probably a bit shorter distribution, something like that, say. So this one has something like that. This one has a wider sigma, but it's got the same mu. It'd be too high at the edges here and too low in the middle. So then we could add up the differences between all of our measurements and all of our estimates. We've got all of these places where we underestimate here and all of these places where we overestimate here. And we could add up those differences, or in fact the squares of them, to get a measure of the goodness or badness of the fit. And we'll look in detail at how we do that once we've done all the vectors work and once we've done actually all the calculus work. Then we could plot how that goodness varied as we change the fitting parameters sigma and mu. And we get a plot like this. So if we had our correct value, our best possible value for mu here, and our best possible value for the width sigma here, we could then plot for a given value of mu and sigma what the difference was. So if we were at the right value, we'd get a value of goodness where the sums of the squares of the differences was 0. And if mu was too far over, if we had misestimated mu and we'd got the distribution shifted over, i.e. the width was right but we had some wrong value of mu there, then we get some value of all the sums of the squares of the differences of our goodness being some value here that was higher. And it might be the same if we went over the other side and we had some value there. And if we were too wide, we'd get something there, or too thin, we'd get something that was too thin like that. Something like that, say. So we'd get some other value of goodness. And we could imagine plotting out all of the values of where we had the same value of goodness or badness for different values of mu and sigma. And we could then do that for some other value of badness, and we might get a contour that looked like this, and another contour that looked like this, and so on and so forth. Now, say we don't want to compute the value of this goodness parameter for every possible mu and sigma. We just want to do it a few times and then find our way to the best possible fit of all. So say we started off here with some guess that was too big a mu and too small a width. We thought people were taller than they really are and that they were tighter packed in their heights than they really are. Well, what we could do is we could say, well, if I do a little move in mu and sigma, then does it get better or worse? And if it gets better, well, we'll keep moving in that direction. So we could imagine making a vector of a change in mu and a change in sigma. And we could have our original mu and sigma there, and we could have a new value u prime sigma prime, and ask if that gives us a better answer, if it's better there, or if mu prime, sigma prime took us over here, if we were better or worse there, something like that. Now actually, if we could find what the steepest way down the hill was, then we could go down this set of contours, this sort of landscape here, towards the minimum point, towards the point where we get the best possible fit. And what we're doing here, these are vectors. These are little moves around space. They're not moves around a physical space, they're moves around a parameter space, but it's the same thing. So if we understand vectors and we understand how to get down hills, that sort of curviness of this value of goodness, that's calculus, then once we've got calculus and vectors, we'll be able to solve this sort of problem. So we can see that vectors don't have to be just geometric objects in the physical world of space. They can describe directions along any sorts of axes. So we can think of vectors as just being lists. If we thought of the space of all possible cars, for example, so, here's a car, there's its back, there's its window, there's the front, something like that. There's a car, there's the window. We could write down in a vector all of the things about the car. We could write down its cost in euros. We could write down its emissions performance in grams of CO2 per 100 kilometers. We could write down its NOx performance, how much it polluted our city and killed people due to air pollution. We could write down its Euro NCAP star rating, how good it was in a crash. We could write down its top speed and write those all down in a list that was a vector. That'd be more of a computer science view of vectors, whereas the spatial view is more familiar from physics. In my field, metallurgy, I could think of any alloy as being described by a vector that describes all of the possible components, all the compositions of that alloy. Einstein, when he conceived relativity, conceived of time as just being another dimension. So space-time is a four-dimensional space, 3 dimensions of meters, and 1 of time in seconds. And he wrote those down as a vector of space-time, of x, y, z, and time, which he called space-time. When we put it like that, it's not so crazy to think of the space of all the fitting parameters of a function, and then of vectors as being things that take us around that space. And what we're trying to do then is find the location in that space where the badness is minimized, the goodness is maximized, and the function fits the data best. If the badness surface here was like a contour map of a landscape, we're trying to find the bottom of the hill, the lowest possible point in the landscape. So to do this well, we'll want to understand how to work with vectors and then how to do calculus on those vectors in order to find gradients in these contour maps and minima and all those sorts of things. Then we'll be able to go and do optimizations, enabling us to go and work with data and do machine learning and data science. So, in this video, we've revisited the problem of fitting a function to some data, in this case, the distribution of heights in the population. What we've seen is that the function we fit, whatever it is, has some parameters, and we can plot how the quality of the fit, the goodness of the fit, varies as we vary those parameters. Moves around these fitting parameter space are then just vectors in that space of fitting parameters. And therefore we want to look at and revisit vector maths in order to be able to build on that and then do calculus and then do machine learning. So we have these things called vectors, like this guy here. What we want to do first is get an idea of what makes a vector a vector. What we'll do in this video is explore the operations we can do with vectors, the sort of things that we can do with them that define what they are and the sort of spaces they can apply to. So a vector we can think of as an object that moves us about space, like this guy here. This could be a physical space or a space of data. At school, you probably thought of a vector as something that moved you around a physical space. But in computer and data science, we generalize that idea to think of a vector as maybe just a list of attributes of an object. So we might think of a house, say. So here's a house. And this might have a number of attributes. We could say it was 120 square meters in floor area. It might have 2 bedrooms, say. It might have 1 bathroom. That would be sort of sensible. And it might be worth 150,000 euros, say. And I could write that down as the vector, 120 square meters, 2 bedrooms, 1 bathroom, and 150,000 euros. And this, that is, while in physics we think of this as being a thing that moves us about space, in data science we'd think of this vector as being a thing that describes the object of a house. So we've generalized the idea of moving about space to include the description of the attributes of an object. Now, a vector is just something that obeys two rules. Firstly, addition, and secondly, multiplication by a scalar number. We'll do this first, thinking of a vector as just a geometric object starting at the origin. So something like this. So we'll get a vector R there. Vector addition is then when we just take another vector. So let's take another vector like this guy here. Let's call him S. And where we put S on the end of R. So then that's S. And therefore, if we put S on the end of R, we get a sum that's R then going along S. We'll call that guy R plus S. Now, we could do this the other way around. We could do S and then R, and that would be S plus R. So we go along S and along that way. And that would be S plus R there, S plus R. And we see that they actually give us the same thing, the same answer. So R plus S is equal to S plus R. So it doesn't matter which way round we do the addition. So the other thing we want to be able to do is scalar multiplication, that is to scale vectors by a number. So a number A, say, making it twice as long or half as long, something like that. So we'd say that, say, 3R was doing R 3 times, so that would be 3R there, where A was 3. Or we could do a half R, which would be something like that. The only tricky bit is what we mean by a minus number, and by minus R, we'd mean going back the other way by a whole R. So we take R, we go back the other way, the same distance there. That would be minus R. So in this framework, minus means go back the other way. At this point, it's convenient to define a coordinate system. So let's define space by two vectors. Let's call the first one that takes us left, right, and is of unit length, length 1. Let's call that a vector I. We'll have another vector here that goes up, down, a vector j that's also of unit length 1. And then we'd say, just use our vector addition rules. If we wanted a vector r here, something like this, that was 3, 2, by which we mean we go 3 i's, 1 I, 2 I, 3 i's, and then 2 j's. So we go 3 i's plus 2 j's, and that gives us a vector r here, just from our vector sum. And what we mean in the 3, 2 is do 3 i's added together, or a scalar multiple of 3 i's, and then do a scalar multiple of 3 j's as a vector sum. And that's what we mean by a coordinate system and defining R as being 3, 2. So that if I have another vector, S, let's say S is equal to minus 1 i's and 2 j's. That is, it takes us back 1 I and up 2 j's. So that's S. Then R plus S would be that. We just put S on the end of R. And then R plus S is going to be, therefore, that total vector. That's going to be R plus S. And we can just add up the components, right? So R is 3 i's, and S takes us back 1. So it's 3 plus minus 1 gives us 2 i's. And in the j's, R takes us up 2, and S takes us up another 2. So that's a total of 4 j's. So we can just add up the components when we're doing vector addition. So we can see that because we're doing this component by component, then vector addition must be what's called associative. Formally, what this means is that if we have 3 vectors, R, S, and another one, T, it doesn't matter whether we add R plus S and then add T, or whether we add R to S plus T. It doesn't matter where we put the bracket. We can do this addition and then that one, or we can do this addition and then that one. So a consequence of it not mattering what order we had, so S plus R is equal to R plus S, we can also see that therefore it doesn't matter what order we do the additions in if we've got 3, and that's called associativity. That's associative. That's formally that definition. And vector addition, we can see when we're adding it up like this, will be associative. So I've just got rid of the S's and so on, so we can talk about another issue, which is in a coordinate system, what do we mean by multiplication by a scalar? So if we want to take a multiplication by a scalar, say 2, then we define this to mean that 2R would be equal to 2 times the components of R. So 2 times 3 for i's, and 2 times 2 for the j's, because we've got 2 there, multiplied by 2, and that will give us 6, 4. So 2r would be doing r and then doing another r, so that would be 2r, which would be the vector 6, 4. Go along 3 i's, 4, 5, 6 i's, and up 4 j's. Now, you need to think about another question, which is minus r. So r is this, minus r is then that, which will be minus 3 minus 2. That will be minus r. So then we see sort of obviously, kind of, that r plus minus r is equal to 3 plus minus 3 on the i's and 2 plus minus 2 on the j's, which is equal to 0, 0. So if we do r and then add minus r, we end up back at the origin, duh. Therefore, we've defined what we mean by vector subtraction here. Vector subtraction is just addition of minus 1 times whatever I'm doing, putting after the minus sign. So if we think of another vector s, we had s was minus 1, 2 before, right? Minus 1i plus 2j's. So then r minus s would be this. So that's minus s there is equal to go along 1 on the i's and minus 2 on the j's. So r minus s, add up the components, r minus s, let's switch to an addition. So r minus s is this vector here, that's r minus s. If we add up the components of that, it's 3i's plus 1, 3 plus 1 on the i's, and 2 plus minus 2 on the j's. So that gives us the vector 4, 0. So if we do r is go along 3, and minus s is go along 1, we've got a total of 4. And if r is go up 2, and minus s is go down 2, we've ended up going up, down 0 in total. So then we've not only done addition by components, we've done now what we mean by vector subtraction as well, as being addition of a negative 1 multiple of the thing that we're doing the minus by. And that's vector subtraction and addition by components. So let's come back to the house example for a moment. So we said we had a house, that's my house, that was 120 square meters, 2 bedrooms, 1 bathroom, and 150,000 euros. So if I put the units in, that's square meters, that's its number of beds, that's its number of baths, and that's its thousands of euros that it's worth. So 2 houses now is equal to the vector addition of those things is equal to 2, and the way we're defining vector addition, times 120 to 150, which would be equal to 240 4 to 300. So we'd say that in this scheme, the way we're defining it, then 2 houses would be 240 square meters, that makes sense. 4 bedrooms, 2 bathrooms, and worth 300,000 euros if I bought 2 houses identically next to each other. And that would be a scalar multiple or an addition of one house to another. Yeah, 1 house plus 1 house. And we could keep on doing that with 3 houses or differently shaped houses or whatever it was, or negative houses. The way we've defined vectors, that will still apply to these objects of houses. So that's vectors. We've defined 2 fundamental operations that vectors satisfy. That is addition, so like r plus s here, and multiplication by a scalar, so like 2r here and minus s here. And we've explored the properties that those imply, like associativity of addition and subtraction, what subtraction really means of vectors, r plus minus s being r minus s. And we've noticed that it can be useful to define a coordinate system in which to do our addition and scaling, so like 3, 2 here, using these fundamental basis vectors, these things that define the space, I and j, which we call the basis vectors, or the things that define the coordinate system. We've also seen that although perhaps it's easiest to think of vector operations geometrically, we don't have to do it in a real space. We can do it with vectors that are data science lists of different types of things, like the attributes of a house. So that's vectors. That's all the fundamental operations. In this module, what we're looking at is the sort of things we can do with vectors. First, we can look at their modulus or magnitude. We can look at a way to combine vectors together to get a number called the dot product, which will take us on to find the scalar and vector projections. That will then take us on to looking at the vectors that we use to define the space, the basis vectors, and at linear independence and linear combinations. And that will wrap up Module 2. This is hopefully going to be a good work. We'll get all set with some nice problems and exercises to try this stuff out. This is the main module on vectors. After this, in the next modules, we'll move on to matrices. So, we've got stuff to do. Let's get started with the next video on the modulus and the dot product. So, we've looked at the two main vector operations of addition and scaling by a number. And those are all the things we really need to be able to do to define what we mean by a vector, the mathematical properties a vector has. Now we can move on to define two things. The length of a vector, also called its size, and the dot product of a vector, also called its inner, scalar or projection product. The dot product is this huge and amazing concept in linear algebra with huge numbers of implications, and we'll only be able to touch on a few parts of it here, but enjoy. It's one of the most beautiful parts of linear algebra. So, when we defined a vector initially, this guy R, we did it without reference to any coordinate system. In fact, as a geometric object, this thing just has two properties. Its length here, and its direction, which is going this way, as opposed to this way or this way. So irrespective of the coordinate system we decided to use, we want to know how to calculate those two properties, its length and the direction it's going in. Now, if the coordinate system that we use to define R use these two vectors I and j, we can say that R is equal to AI plus BJ, or is equal to AB, the way we were writing it in the last video. Now, if we want to know the length of R, well, we can draw a triangle, right? And then we can use Pythagoras' theorem. So we've got AI's going along this way, and we've got BJ's going along this way. And if I and J are both of unit length, that is, the length of those is just A here and B here, where this vertical lines on either side means the size. So then we can use Pythagoras' theorem just for a triangle, where we've got A there, B there. This length then, from Pythagoras' theorem, will be the square root of A squared plus B squared. And we can say that that's equal to the length of R. It's the square root of A squared plus B squared. So the length of R is equal to AB. So R is that. And the length of R we define to be equal to the square root of A squared plus B squared. Now, we've done this for two spatial directions defined by the unit vectors I and j, and those are at right angles to each other. But this definition of the size of a vector is more general than that. It doesn't matter if the different components of the vector are dimensions in space, or even things with different physical units like bedrooms and bathrooms, or length and time and price. We still define the size of a vector through the sums of the squares of its components, all square rooted. The next thing we're going to do is define the dot product, which is one way of several, of multiplying two vectors together. So we've got two vectors here, R and S. And I'm going to make this a bit more general, actually. I'm going to give them components. So I'm going to call it Ri, Rj. So R has a component I, in this case 3, and a component j, in this case 2, in the j directions and the I directions, respectively. And S, we can do the same thing. We can say S has components Si and Sj. So then we define the dot product, and the dot product is just a number, like 3. It doesn't have any associated spatial dimension or direction along the vectors I and j. We'll define the dot product R dot S to be equal to what happens if I multiply Ri by Si and add it to Rj times Sj. So in this case, that gives me, it gives me 3 there times minus 1 plus 2 times 2. So that gives me 3 plus 4, minus 3 plus 4, which is equal to 1. So the dot product of r plus dot s in this case is minus 3 plus 4, which is 1. Now, we can go on to look at one property of the dot product, which is that it's commutative. So commutative, which is spelt commutative. And that means that r dot s is equal to s dot r. It doesn't matter which way round we do it. And we can see that fairly simply, because if we just switch that around, we'd have si times ri plus sj times rj, and that's going to be the same number. So we can see immediately, fairly trivially, that the dot product is commutative. It doesn't matter which order we do it in. Now the second property we're going to prove is that the dot product is distributive over addition. So if I have some third vector, let's take some third vector t, what being distributive means is that r dot s plus t is the same as r dot s plus r dot t. That is, we can multiply out this bracket in the way that we would if they were just numbers. And we're going to prove this in a general case for any dimension vectors. So we'll have a vector r is equal to components r1, r2 for i's and j's all the way up to some dimension rn. And s is some other vector s1, s2 all the way up to some bit sn. And t is another one which is equal to t1, t2 all the way up to some component tn. And then r dot s plus t is going to be equal to r1 times s1 plus t1 plus r2 for the second dimension times s2 plus t2 plus all the other dimensions plus rn times sn plus tn, if I multiply it out for all the dimensions. And then I can just multiply out those brackets. That's going to be r1 s1 plus r1 t1 plus, now multiply out this bracket, r2 s2 plus r2 t2 plus all the dots, rn sn plus rn tn. And if I collect together the rs terms, I've got r1 s1, r2 s2 and rn sn, so that's r dot s. And if I collect all the t terms together, I've got r dot t. So we've demonstrated that this distributive property is in fact true. So it's also kind of obvious that if we multiply a vector through by a scalar, so if we take a times s, that's our other fundamental operation was multiplying by a scalar, and then do the dot product on that, so we do r dot as, then that's going to be equal to a times r dot s. Because if we take this s here, when we do this, if we multiply s here through by a number a, we're just going to get the number a come out of all the components. So that's going to be, if we do it, ri times a si plus rj times a sj. That's the left-hand side. And that's equal to a times ri si plus rj sj. So that is, this property is called that it's associative over scalar multiplication. Over scalar, that's the number a, multiplication. So we've got three properties. We've got it's associative over scalar multiplication, the dot product is distributive, and it's commutative. Now the last thing we need to do is draw the link between the dot product and the size of the vector. This is quite surprising. If we take r and dot it with itself, we get ri times ri plus rj times rj, plus all the other components, whatever they are. So that's equal to ri squared plus rj squared. But we said that the size of the vector was the square root of that. So r dot r is equal to the size of the vector squared. So that is, the size of the vector is just given, in some senses, by r dotted with itself, which is quite cool. Let's take the cosine rule from algebra, which you'll remember probably vaguely from school. And that said, if we had a triangle with sides A, B, and C, then what the cosine rule said was that c squared was equal to a squared plus b squared minus 2ab times the cos of the angle between a and b, cos that angle theta there. Now, we can translate that into our vector notation. If we called this vector r here, and we called this vector s here, then this vector would be minus s plus r. So that vector would be r minus s plus r. So we could say that c squared was the modulus of r minus s squared, and that would be equal to the modulus, the size of r squared, plus the size of s squared, minus 2 mod r mod s cos theta. Now, here's the cool bit. We can multiply this out using our dot product, because we know that the size of r minus s squared is equal to r minus s dotted with itself. Now, that's just that. And we can multiply that out, and then we'll compare it to this right-hand side here. So r minus s dotted with r minus s, well, that's going to be, if we need to figure out how to multiply that out, that's going to be equal to r dotted with r, and then take the next one, minus s dotted with r, minus s dotted with r again. If you take that minus s and that r, minus s dotted with r again, and then minus s dotted with minus s. So that is, we've got the modulus of r squared here, and we dot r with itself, minus twice s dotted with r, and then minus s dotted with minus s, well, that's going to be the size of minus s squared, which is just the size of s squared. And then we can compare that to the right-hand side, and when we do that comparison, compare that to the right-hand side, the minus r squareds are going to cancel, the r squareds even, the s squareds are going to cancel, and so we get a result, which is that minus twice s dotted with r is equal to minus twice modulus of r, modulus of s, cos theta. That is, and then we can lose the minus sign, right? The minus signs will cancel out, just multiply through by minus 1. So, and then the 2's we can cancel out again. So we can say that the dot product, r dot s, just to put it in a more familiar form, is equal to mod r mod s cos theta. So what we found here is that the dot product really does something quite profound. It takes the size of the two vectors, if these were both unit length vectors, those would be 1, and multiplies by cos of the angle between them. It tells us something about the extent to which the two vectors go in the same direction. Because if cos theta, if theta was 0, then cos theta would be 1, and r dot s would just be the size of the two vectors multiplied together. If the two vectors, on the other hand, were at 90 degrees to each other, if they were, r was like this, and s was like this, and the angle between them, theta, was equal to 90 degrees, cos theta, cos of 90, is 0, and then r dot s is going to be, we can immediately see, r dot s is going to be some size of r, some size of s, times 0. So if the two vectors are pointing at 90 degrees to each other, if they're what's called orthogonal to each other, then the dot product's going to give me 0. If they're both pointed in the same direction, say S was like that, and the angle between them is 0, cos of 0 is equal to 1. And then R dot S is equal to the mod R times mod S, just the multiplication of the two sizes together. Last fun one here, is that R and S are in opposite directions. So let's say S was now going this way, and the angle between them was 180 degrees. Cos of 180 degrees is equal to minus 1. So then R dot S would be equal to minus the size of R times the size of S. And so what the dot product here really does with this cos, it tells us when we get the minus sign out that they're going in opposite directions. So there's some property here in the dot product that we've derived by looking at the cosine rule that we've derived here. When the dot product's 0, they're at 90 degrees to each other, they're orthogonal. When they're going the same way, we get a positive answer. When they're going more or less in opposite directions, we get a negative answer for the dot product. Now, there's one last thing to talk about in this segment, which is called projection. And for that, we'll need to draw a triangle. So if I've got a vector R and another vector S, now, if I take a little right-handed triangle, drop a little right-handed triangle down here, where this angle's 90 degrees, then I can do the following. If I can say that, if this angle here is theta, that cos theta is equal to, from SOHCAHTOA, is equal to the adjacent length here over the hypotenuse there. Adjacent over the hypotenuse. That is, and this hypotenuse is the size of S. So it's the adjacent over the size of S there. Now, if I compare that to the definition of the dot product, I can say that R dotted with, we'll have fun with colours, dotted with S is equal to mod R, size of R, times the size of S, times cos theta. Cos theta. But the size of S times cos theta, if I put S up here, I just need to put my theta in there. Cos theta is just that adjacent side. So that's just that adjacent side here in the triangle. So the adjacent side here is just kind of the shadow. If I had light coming down from here, it's the shadow of S on R, that length there. It's kind of a shadow cast if I had a light at 90 degrees to R shining down on S. And that's called the projection. So what the dot product gives us is it gives us the projection here of S onto R times the size of R. One thing to notice here is that if S was perpendicular to R, if S was pointing this way, it would have no shadow. That is, if cos theta was 90 degrees, that shadow would be 0. The cos theta would be 0 here, and I get no projection. The other thing the dot product gives us is it gives us the size of R times some idea about the projection of S onto R, the shadow of S onto R. So if I divide the dot product R dot S by the length of R, just bring the R down here, I get mod S cos theta. I get that adjacent side. I get a number which is called because r dot s is a number and the size of r is a number, and that's called the scalar projection. And that's why the dot product is also called the projection product, because it takes the projection of one vector onto another. We just have to divide by the length of r. And if r happened to be a unit vector, or one of the vectors we use to define the space of length 1, then that would be of length 1, and r dot s would just be the scalar projection of s onto that r, that vector defining the axes or whatever it was. Now, if I want to remember to encode something about r, which way r was going, into the dot product or into the product, I could define something called the vector projection. And that's defined to be r dot s over mod r dotted with itself, so r dot r mod r squared. So that's r dot s over r dot r, if you like, because mod r squared is equal to r dot r. And we multiply that by the vector r itself. So that's dot product's just a number, these sizes are just a number, and r itself is a vector. So what we've done here is we've taken the scalar projection r dot s over r, this guy, that's how much s goes along r, and we've multiplied it by r divided by its length. So we've multiplied it by a vector going the direction of r, but that's been normalized to have a length 1. So that vector projection is a number times a unit vector that goes in the direction of r. So if r, say, was some number of lengths, the vector, that would be r divided by its size, say, if that was a unit length vector I've just drawn there. And the vector projection would be that number s dot r, that adjacent side, times a vector going in the unit length of r. So that's, if you like, the scalar projection also encoded with something about the direction of r, just a unit vector going in the direction of r. So we've defined a scalar projection here, and we've defined a vector projection there. So, good job. This was really the core video for this week. We've done some real work here. We've found the size of a vector, and we've defined the dot or projection product. We've then found out some mathematical operations we can do with the dot product. That it's distributive over vector addition and associative with scalar multiplication, and that it's commutative. We've then found that it finds the angle between two vectors, the extent to which they go in the same direction. And then it finds the projection of one vector onto another. That's kind of how one vector will collapse onto another, which is what we'll explore in the next 2 videos. So, good work. Now's a good time to pause and try some examples that put all this together and give it all a workout and a bit of a try before we move on. Now, so far, we haven't really talked about the coordinate system of our vector space, the coordinates in which all of our vectors exist. But it turns out that in doing this thing of projecting, of taking the dot product, we're projecting our vector onto one which we might use as part of a new definition of the coordinate system. So in this video, we'll look at what we mean by a coordinate system, and then we'll do a few cases of changing from one coordinate system to another. So, remember that a vector, like this guy r here, is just an object that takes us from the origin to some point in space, which could be some physical space, or it could be some space of data, like bedrooms and thousands of euros for the house, or something like that. What we haven't talked about so far, really, is the coordinate system that we use to describe space. So, we could use a coordinate system defined by these 2 vectors here. I'm going to give them names. We called them I and j before. I'm going to give them names E1 and E2. I'm going to define to be of unit length, so I'm going to give them a little hat, meaning they're of unit length. And I'm going to define them to be the vectors 1, 0 and 0, 1. And if I had more dimensions in my space, I could have E3 hat, E4 hat, E5 hat, E a million hat, whatever. Here the instruction then is that R is going to be equal to doing a vector sum of 2 E1s or 3 E1s and then some number of E2. So we'll call it doing 3 E1s hats plus 4 E2 hats. And so we'll write it down as a little list, 3, 4. So R is the 3, 4 here is the instruction to do 3 E1 hats plus 4 E2 hats. But if you think about it, my choice of E1 hat and E2 hat here is kind of arbitrary. It depends entirely on the way I set up the coordinate system. There's no reason I couldn't have set up some coordinate system at some angle to that. Or even use vectors to find the axes that weren't even at 90 degrees to each other and were of different lengths. I could still have described R as being some sum of some vectors I used to define the space. So I could have, say, another set of vectors B, and I'll call B1 here in the vector 2, 1, and I could have another vector here, B2, as the vector minus 2, 4. And I've defined it in terms of the coordinates E, and I could then describe R in terms of you're using those vectors B1 and B2. It's just the numbers in R would be different. So we call the vectors we use to define the space, these guys E or these guys B, we call them basis vectors. So the numbers I've used to define R only have any meaning when I know about the basis vectors. So R referred to these basis vectors E is 3, 4. But R referred to the basis vectors B also exists. We just don't know what the numbers are yet. So this should be kind of amazing. R, the vector R, has some existence in a deep sort of mathematical sense, completely independently of the coordinate system we use to describe the numbers in the list describing R. R, the vector that takes us from there, from the origin to there, still exists independently of the numbers used in her. Which is kind of neat, right? Sort of fundamentally sort of idea. Now, if the new basis vectors, these guys B, are at 90 degrees to each other, then it turns out the projection product has a nice application. We can use the projection or dot product to find out the numbers for R in the new basis B, so long as we know what the B's are in terms of E. So here I've described B1 as being 2, 1, as being E1 plus E2, twice E1 plus 1 E2. And I've described B2 as being minus 2 E1s plus 4 E2s. And if I know B in terms of E, I'm going to be able to use the projection product to find R described in terms of the B's. But this is a big if. The B1 and B2 have to be at 90 degrees to each other. If they're not, we end up being in big trouble and need matrices to do what's called a transformation of axes from the E to the B set of basis vectors. We'll look at matrices later, but this will help us out a lot for now. Using dot products in this special case where the new basis vectors are orthogonal to each other is computationally a lot faster and easier. It's just less generic. But if you can arrange the new axes to be orthogonal, you should, because it makes the computations much faster and easier to do. So you can see that if I project R down onto B1, so I look down from here and project down at 90 degrees, I get a length here for the scalar product, and that scalar projection is the shadow of R onto B1, and a number of the scalar projection describes how much of this vector I need. And the vector projection is going to actually give me a vector in the direction of B1 of length equal to that projection. Now if I take the vector projection of R onto B2, going this way, I'm going to get a vector in the direction of B2 of length equal to that projection. And if I do a vector sum of that vector projection plus this guy's vector projection, I'll just get R. So if I can do those two vector projections and add up their vector sum, I'll then have RB being the numbers in those two vector projections. And so I've found how to get from R in the E set of basis vectors to the B set of basis vectors. Now, how do I check that these two new basis vectors are at 90 degrees to each other? I just take the dot product. So we said before the dot product cos theta was equal to the dot of two vectors together, so B1 and B2, divided by their lengths. So if B1 dot B2 is 0, then cos theta is 0, and cos theta is 0 if they're at 90 degrees to each other, if they're orthogonal. So I don't even need to calculate lengths, I'll just calculate the dot product. So B1 dot B2, here, I take 2 times minus 2, and I add it to 1 times 4, which is minus 4 plus 4, which is 0. So these two vectors are at 90 degrees to each other. So it's going to be safe to do the projection. So having talked through it, let's now do it numerically. So if I want to know what are described in the basis E, and R's pink, right? So if I take R in the basis E, and I'm going to dot him with B1, and the vector projection divides by the length of B1 squared. So R in E dotted with B1 is going to be 3 times 2 plus 4 times 1, 4 times 1, divided by the length of B1 squared. So that's the sum of the squares of the components of B. So that's 2 squared plus 1 squared. So that gives me 6 plus 4 is 10 divided by 5, which is 2. So this projection here is of length 2 times B1. So that projection there, that vector, is going to be 2 times B1. So that is, in terms of the original set of vectors B, original vectors E, RE dot B1 over B1 squared times B1 is the vector, is 2 times the vector 2, 1, is the vector 4, 2. And I can do then now this projection onto E2, so I can do RE dotted with B2 and divide by the length of B2 squared. And RE dot B2 is 3 times minus 2 plus 4 times 4 divided by the length of B2 squared, which is minus 2 squared plus 4 squared. So that's 3 times minus 2 is 6, minus 6 plus 4 times 4 is 16. So that's minus 6 plus 16 is 10. Divided by this length here is 4 squared is 16, 2 squared is 4, so 20. So that's equal to a half. So this vector projection here is that guy times B2. So that's RE dot B2 over the modulus of B2 squared. That's my half times the vector B2. So that's a half times the vector B2, which is minus 2, 4. Now if I add those two together, 4, 2, this bit, that vector projection, plus this vector projection, so this guy is going to be a half B2, plus half minus 2, 4 is minus 1, 2. If I add those together, I've got 3, 4, which is just my original vector R, 3, 4, in the basis E. So in the basis of B1 and B2, RB is going to be 2, a half. Very nice, 2, a half. So actually in the basis B, it's going to be 2, a half there. So RB is 2 times B1 plus a half times B2. Very nice. So I've converted from the E set of basis vectors to the B set of basis vectors, which is very neat, just using a couple of dot products. So this is really handy, this is really cool. We've seen that our vector describing our data isn't tied to the axes that we originally used to describe it at all. We can redescribe it using some other axes, some other basis vectors. So the basis vectors we use to describe the space of data and choosing them carefully to help us solve our problem will be a very important thing in linear algebra and in general. And what we've seen is we can move the numbers in the vector we use to describe a data item from one basis to another. We can do that change just by taking the dot or projection product in the case where the new basis vectors are orthogonal to each other. So we've seen how we don't just have to have basis vectors that are normal 1, 0 and 0, 1, the so-called natural basis here. We can have different basis vectors that redefine how we move about space. In this video, what we're going to do is we're going to define what we mean by a basis, by a vector space, and by the term linear independence, which is going to let us understand how many dimensions our vector space actually has. So first, let's define what we mean by a basis. A basis is a set of n vectors that are not linear combinations of each other, which means they're linearly independent and that they span the space that they describe. The space is then n-dimensional. The first criteria I can write down by saying that if they're linearly independent, then I can't write any of them by taking some combination of the others. For example, if I had a candidate B3, it would be linearly dependent on the basis vectors B1 and B2 if I could take some combination of them, A1 B1s plus, say, A2 B2s, where A1 and A2 are numbers. If I could take a linear combination of B1 and B2, like this, and find B3, then B3 would be linearly dependent on B1 and B2. It wouldn't be an independent vector. So it's some vector. I can sketch it out by doing something like this. If I've got B1 here and say, I don't know, B2 here, if B3 I can find by some combination of B1 and B2s, it must lie in the same plane as B1 and B2. Right, the plane of my board. If B3 is actually lying out of the plane here, I couldn't make the out-of-plane component of it using my B1s and B2s. So B3 would then be linearly independent of B1 and B2. This equal sign I couldn't ever make true. And then B3 would lie outside of the plane. I then have three basis vectors. Those three would then define a three-dimensional vector space. And I could get anywhere in 3D space with them. And then if I had another basis vector, B4, that wasn't a linear combination of B1, B2, and B3, then B4 would then let me have a four-dimensional space, and so on, to up to as many dimensions as I like. Then a vector is in the vector space, spanned by B1 and B2, if it can be found by a linear combination of B1s and B2s. Now, notice what my basis vectors B don't have to be. They don't have to be unit vectors, by which I mean vectors of length 1. And they don't have to be orthogonal at 90 degrees to each other, normal to each other. But everything is going to be much easier if they are. So if at all possible, you want to construct what's called an orthonormal basis vector set, where they're all at 90 degrees to each other and all of unit length. Now let's think about what happens when we map from one basis to another. The number line of the axis of the original grid then projects down onto the new grid, like here, and potentially has different values on that grid. But the projection keeps the grid being evenly spaced. Therefore, any mapping that we do from one set of basis vectors, one coordinate system, to another set of basis vectors, another coordinate system, keeps the vector space being a regularly spaced grid where our original vector rules of vector addition and multiplication by a scalar still work. It doesn't warp or fold space, which is what the linear bit in linear algebra means geometrically. Things might be stretched or rotated or inverted, but everything remains evenly spaced and linear combinations still work. Now, whether new basis vectors aren't orthogonal, then to do the change from one basis to another, we won't just be able to use the dot product anymore. We'll have to use matrices instead, which we'll meet in the next module. So that's the formal definition of what we mean by a basis and by linear independence. For example, say I have a bunch of 2D data points like this, and say they all more or less lie on a straight line, right? We can kind of see that. These guys all more or less lie on a line that's going to be something like that. I can imagine redescribing that data by mapping them onto that line and then saying how far they're along that line. So I can map this guy down onto the line, and I can say the origin maps down there, and I can then say this data point is that far along the line. And he's also, so he's that far along the line, there, and he's this far away from the line. So I've got two dimensions here, how far I am along the line, and how far I am from the line. And these guys, they're all slightly different distances from the line. Now, there's a little bit of an argument in stats as to whether we do the distance that way vertically or that way as a projection of the distance from the line. But it's sort of a theoretical argument. But notice that this distance from the line is effectively a measure of how noisy this data cloud is. If they are all tight on the line, they'd all be very small distances away. And if they were all quite spread, they'd be quite big distances away. So this distance from the lineness is in fact the noise. And that's information that isn't very useful to us, so we might want to collapse it. Except that noise dimension tells me how good this line fit is. If the best fit line was all skewed, was all wrong, I get a much bigger numbers for the noisiness. And if the best fit line was as good as possible, I get the minimum possible number for the noisiness. So that noise dimension contains information that's going to tell me how good my fit is. So when I'm doing data science, it tells me how good my fit to my data is. And the way I've defined these two directions along the line and away from the line, they're orthogonal to each other. So I can use the dot product to do the projection to map the data from the xy space onto the space of the line, along the line and away from the line. Which is what we learned to do in the last little segment. Now, if we're thinking about a neural network in machine learning that recognises faces, say, maybe I'd want to make some transformation of all the pixels in a face into a new basis that describes the nose shape, the skin hue, the distance between the eyes, those sorts of things, and discard the actual pixel data. So the goal of the learning process of the neural network is going to be to somehow derive a set of basis vectors that extract the most information-rich features of the faces. So, in this video, we've talked about the dimensionality of a vector space in terms of the number of independent basis vectors that it has. And we found a test for independence that the set of vectors are independent if one of them are a linear combination of the others. We've talked more importantly about what that means in terms of mapping from one space to another and how that's going to be useful in data science and machine learning. So, back at the start of the course, we encountered the apples and bananas problems. How to find the price of things when we only have the total bill. And we've looked at vectors so far, and now we're going to look at matrices. And these are objects that rotate and stretch vectors, but they're also objects that let us solve these sorts of problems. So let's go back to that apples and bananas problem. So I walk into a shop and I buy 2 apples and 3 bananas, and that costs €8. So we're saying 2 apples and 3 bananas cost €8. Now, so I go into the shop on another day and I buy 10 apples and 1 banana, and that costs me, or the shopkeeper charges me, €13. And I want to discover what the price for 1 apple and 1 banana is, so I can decide which offers better value, or even just predict my bill. Now, you might say this is silly. What shop doesn't have sticker prices after all? But actually in business, with complicated products and service agreements and hire purchase, this sort of thing, price discovery, happens all the time. You know, think about what happens when you buy a car, for instance. Now, these are just simultaneous equations, but I can write them down in another way. So the way I would write this down with matrices would be as follows. I'd write it down as this matrix, what I'm now calling a matrix, an object with numbers in 2, 3, 10, 1. AB equals 8, 13. And these things I call matrices. This is a 2 by 2 matrix. This is a 2 row by 1 column matrix. And this is another 2 row by 1 column matrix. And the instruction here is to multiply this out in the following way. So I would multiply the elements in the rows by the elements in the column. So I'd multiply 2 by A plus 3 times B, that's that row times that column, and I'd say that equaled the top row on the right-hand side. And I'd do the same for the next row. That row times that column is 10A plus 1B is equal to the row on the bottom on the right-hand side. And that looks like my two simultaneous equations. But this is really handy because these things, notice, look like vectors. So this matrix operates on this vector to give this other vector. And my question is, what vector transforms to give me this guy on the right? Now, let's look at what happens if I multiply this matrix here by the unit basis vector, the x-axis vector. Well, when I do that multiplication, I'm going to get 2 times 1 plus 3 times 0. And I'm going to get 10 times 1 plus 1 times 0. So I get the vector 2, 10. So what this does is it takes the little unit vector, which we called E1 hat, and it transforms it to another place, which is 2, 10, which is going to be up here somewhere. So that's E1 hat changed, and that's equal to 2, 10. Now, if I do that with the other basis vector, if I do 2, 3, 10, 1 multiplied by 0, 1, then I'm going to get 2 times 0 plus 3 times 1, 10 times 0 plus 1 times 1. I'm going to get 3, 1. So the other basis vector, E2 hat, gets transformed over to 3, 1, which is going to be over here somewhere. So that's E2 changed. I'm using the prime here to indicate changed. 3, 1. So what this matrix does is it moves the basis vectors in some way. It transforms them. It changes the space. So what this matrix 2, 3, 10, 1 does is it's a function that operates on input vectors and gives us other output vectors. And the set of simultaneous equations here is asking, in effect, what vector I need in order to get a transform product at the position 8, 13, in order to get an output of 8, 13. Now, we can see what we mean now by the term linear algebra. Linear algebra is linear because it just takes input values, our a and b, and multiplies them by constants. So everything is linear. And it's algebra, that is, it's a notation describing mathematical objects and a system of manipulating those notations. So linear algebra is a mathematical system for manipulating vectors, and the space is described by vectors. So this is interesting. There seems to be some kind of deep connection between simultaneous equations, these things called matrices, and the vectors we were talking about last week. And it turns out that the key to solving simultaneous equation problems is appreciating how vectors are transformed by matrices, which is the heart of linear algebra. Previously, we introduced the idea of a matrix and related it to the problem of solving simultaneous equations. And we showed that the columns of a matrix just read as what it does to the unit vector along each axis. Now we'll look at different types of matrix and what they do to space, and what happens if we apply one matrix transformation and then another, which is termed composition. Now, because we can make any vector out of a vector sum of the scaled versions of E1 hat and E2 hat, then what that means is that the result of the transformation is just going to be some sum of the transform vectors, which I'm calling E1 hat and E2 hat. This is a bit hard to see, but what it means is that the grid lines of our space stay parallel and evenly spaced. They might be stretched or sheared, but the origin stays where it is, and there isn't any curviness to the space. It doesn't get warped. And that's a consequence of our scalar addition and multiplication rules for vectors. So that is, if I write down the matrix as capital A, and the vector it's transforming as R, whatever it was, AB in our apples and bananas problem, and that gives me some altered version. We said it was 813 before, but I'm going to call it R transformed or R prime. Then we can look at what happens if I do algebra with it. So if I multiply R by some number, just a number, let's call it n, and if I apply A to nr, what I'm saying is that I will get nr prime. And hopefully you can see if I put an n in there, when I multiply it all out, I'm going to get an n in there. Similarly, if I multiply A by the vector r plus s, then I will get ar plus as. So if I get that multiplication, get that, do the whole thing again with another vector and get another vector s and add those two, that will be true. So what I'm saying here is that if I can then think of these as being the original basis vectors, e1 hat and e2 hat, I'll then get some addition of e2 and e1 primed. So if I say that's n e1 hat plus m e2 hat, I'll get a n times e1 hat plus m times a e2 hat, which is n e1 prime plus m e2 primed, which is just the vector sum of some multiple of those. So this space gets transformed, e1 and e2 get moved, and then I can just add up vectors with them. So that's very nice. That means that all of our vector sum rules work. Now, maybe that's a bit confusing, so let's try it with an example. So I've got my matrix A here from my apples and bananas problems of 2, 3, 10, 1, or if we like, the vector 2, 10 and the vector 3, 1. And let's try an example like a vector 3, 2. Now, if I multiply that out, just straightforwardly, as we probably did at school, I've got 2 times 3 plus 3 times 2, so that's 6 plus 6, that's 12. And I've got 10 times 3, which is 30, plus 1 times 2, which is 2, so that's 32. But I could think of that as being 2, 3, 10, 1 times 3 times 1, 0, plus 2 times 0, 1. That is 3 of e1 hat and 2 of e2 hat in a vector sum. Now, I can take the 3 out, so that's 3 times 2, 3, 10, 1 times 1, 0, plus 2 times 2, 3, 10, 1 times 0, 1. And this, we know that this is what happens from e1 hat to get to e1 prime here. So that's 3 times 2, 10. And that's 2 times what happens to e2 hat, and that goes to 3, 1. So that gives us 6 plus 6 is 12, and 30 plus 2 is 32. So it really is true. These rules really do work, and we can think of a matrix multiplication as just being the multiplication of the vector sum of the transformed basis vectors. So pause them for a moment and try that maybe with an example of your own and verify that that really does work, because that's really quite deep. This matrix just tells us where the basis vectors go. That's the transformation it does. It's not a complicated multiplying out thing. We don't need to worry about the mechanics of doing the sum. We can just think of it in terms of what it does to vectors in the space. Now, let's look at some special types of matrices that do simple things, and then we'll think about how to combine them to do complicated things. First, let's think about a matrix that doesn't change anything, a matrix that's just composed of the basis vectors of the space, so 1, 0, and 0, 1. So that, if I multiply it by some vector xy, that's not going to change xy. If I multiply it out, I'm going to get 1 times x plus 0 times y, 0 times x plus 1 times y, xy. So it doesn't change the vector xy. It's just composed of the basis vectors here, and it doesn't change them. And that's called, therefore, the identity matrix. It's the matrix that does nothing and leaves everything preserved, and it's called I. Now, what if I have different numbers along the leading diagonal, something like 3, 0, 0, 2, for instance? Well, that's going to scale the x-axis here by a factor of 3. It's going to go to 3, 0. when I multiply it out. And the y-axis is going to scale by a multiple of 2. It's going to go from 0, 1 to 0, 2. So I've scaled space this way by a factor of 3 and that way by a factor of 2. So my little unit square has gone to being a rectangle from being a square originally. It's scaled up this way 3 times and this way 2 times. And of course, if the scale factor here was a fraction, if it was a third or something, then I'd have squished space that way instead. I'd have gone that way and made it thinner and taller, something like that. So a fraction then squishes space. The next thing to think about is what happens if I've got a matrix where I scale by, say, -1 here on one of the axes. Well, what that's going to do, so the original axes, is it's going to flip them around. So if I've got 1, 0 here, and 0, 1 being the other axis, of course, then that's going to scale the first one over here to being -1, 0. And of the 0, 2 is going to scale the other axis up to 0, 2 here. So my original little cube goes from here to here. So it's changed in area by a factor of 2, 1 times 2, but it's also flipped over. The x-axis has gone over there. Now what does that mean? Well, if I had previously an axis system where I went using my right hand, from my right hand there, that's my first one, that's my second axis, around, and I went counterclockwise. Now I'm going the other way. Now I've got a left-handed coordinate system and I go clockwise, so I need to get my left hand out to describe them now. So I've changed the sense of the coordinate system in flipping it over. Now the other matrix we need to think about, get another pen, is -1, 0, 0, -1, and that inverts everything. It inverts both axes. It takes 1, 0 to -1, 0, and it takes 0, 1 down here to 0, -1. So it flips everything in both coordinates, and that's called an inversion. Another matrix I can think of is 0, 1, 1, 0. That's kind of fun. What that does is it takes I hat 0, 1, 0 here. It takes it to 0, 1, so it takes it to there. 0, 1, that guy goes there. And it takes the other axis, which was there, which was also 0, 1, and it takes it to 1, 0. So what it does is it flips them around. It's like I've put a mirror in at 45 degrees. I could have another mirror, would be 0, -1, -1, 0. And that would take 1, 0 here, and it would make it 0, -1. Would take it down there, 0, -1. And it would take this axis, 0, 1, and it would make it to -1, 0, so it would make it over there. So that's like having a mirror plane in there. And just for completeness, I can think of another two mirrors, and they would be -1, 0, 0, 1. And that flips the x-axis. That's like a vertical mirror. That's that guy. And I can have another one, which would be 1, 0, 0, -1. And that flips the horizontal axis. That flips this guy down, but leaves this guy unchanged. So those are all my mirrors. Another thing I might want to think about are shears. So I wanted to keep E1 hat where it was, 1, 0, but move E2 hat over. So E2 hat is 0, 1. So I wanted to move E2 hat over to here, say. So I wanted to get E2 primed to be equal to 1, 1, say. Now, in which case I can just write down my matrix, right? I can say that E1 becomes itself, 1, 0, and E2 becomes 1, 1. That would be the transformation matrix for that shear. It would be shearing the unit square over from being a little square to being a little parallelogram here, something like that. Of course, I could shear the x-axis as well. I could do some combination of shears, but that's basically how a shear would look. Now, the last sort of shape change I can do after stretches, inversion, mirrors, and shears is a rotation. If I take E1 hat again, and E2 hat, if I rotate them round, well, E1 hat's going to go round here. So E1 primed is going to be equal to 0, 1. And E2 hat is going to go round to here, and E2 primed is going to become minus 1, 0. So that 90-degree rotation there is going to have the transformation matrix 0, 1, minus 1, 0. And in general, I can write down a rotation by an angle here, let's say an angle here of theta. I can write that down as being cos theta, sine theta, sine theta, cos theta. And I need to put a minus sign in here where positive thetas are actually that way. So we did a rotation by minus 90, so sine of minus 90 is minus 1. And that's a general expression for a rotation in 2D. If I wanted to do it in 3D, I need to think about the axis I was doing it along or around. So if I was rotating about Z, I would preserve all of the Zs for a 3D rotation, something like that. But this isn't really a course about matrix rotations and matrix geometry and so on. That would be something like crystallography. This is a course about data science. So we don't need to think too much about rotations. But it is interesting if we need to do things like transform faces, if we're wanting to do facial recognition. We'll want to do these sorts of stretches and mirrors and shears and rotations to faces to get them all facing like that rather than facing like this or at some funny angle that we had from our camera that was looking at somebody. So we do need to do this in data science on occasion. And that's rotations. So what we've described in this video is we've described all the possible sort of changes we can do with a matrix. So now we need to think about how we do a rotation and then a stretch. And that's the next little part. Now, what's the point of telling you about all these different geometric transformations? Well, if you want to do any kind of shape alteration, say of all the pixels in an image or of a face or something like that, then you can always make that shape change out of some combination of rotations, shears, stretches and inverses. That is, if I want to apply a transformation to a vector R, let's call that A1, then that will make some first shape change. Then if I apply some other transformation to that vector that I've then got, what I've done is I've performed first A1 and then A2. Now, maybe this isn't so obvious. Let's slow down and do a concrete example. If I've got a rotation, say, so I take my first set of axes, 1, 0, 0, 1. If I rotate them by 90 degrees, down like this, say, my first axis becomes 0, minus 1, and my second axis is going to become 1, 0. So the transformation matrix for my first transformation, I just write down the column 0, minus 1, 1, 0. That's going to be my first transformation matrix. Now say I take another transformation, well, I do a shear, say. So I take my original axes 1, 0, 0, 1, and I'm going to leave the first axis where it is, so that becomes 1, 0. And I'm going to shear the other axis over like this, and that's going to become 1, 1. So my second transformation matrix is going to be 1, 0, 1, 1. Now, the first transformation takes E1 hat here from 1, 0 to 0, minus 1. So let's see what happens when we apply A2 to that transformed E1 hat. So A2 is 1, 0, 1, 1. And when I multiply that out, I get 1 times 0 plus 1 times minus 1. So that's minus 1. And 0 times 0 plus 1 times minus 1, minus 1, minus 1. So that means that this second transformation, if I do A2 to E1 hat, that's going to take it down here to minus 1, minus 1 when I do A2 to the transformed version of E1 hat. And I can do the same for E2 hat. It's after I did A1, it was at 1, 0. And if I apply A2 to that and multiply it out, I get 1 times 1 plus 1 times 0. And then 0 times 1 plus 1 times 0, 1, 0. So that stays at 1, 0. So my new E2 double primed, if you like. This was E1 double primed. This is E2 double primed. And if I'm being consistent in my notation, that would therefore be E1 primed, and that would be E2 primed. So I take E1, move it to E1 primed, then move it to E1 double prime. Now my axes look like this. So my original little square has become now a little parallelogram over here. And the combination of these transformations, I can just write down what happened. So the combination of those gives me an overall transformation matrix, which is just that column followed by the column of E2 double primed, which is that. So that's equal to A2, A1. Doing first transformation A1, then transformation A2. And this tells us how we do matrix multiplication, for instance. So if I want to know what happens if I do that, so if matrix multiplication, we go about doing the following. If I write down A1, 0, 1, minus 1, 0, and I write down A2, 1, 1, 0, 1, then matrix multiplication, it's a bit like I do with vectors. I multiply the rows times the columns for all the possible rows and columns. So row times column, do that. That'll give me the first entry in what will now be, I can do that for 2 rows, 2 columns here. So I do first row, first column, 1 times 0 plus 0 times minus 1 will give me that, minus 1. And I can then do that for the second column, first row, second column, 1 times 1 plus 1 times 0. I can then do that for the second row, second column, 0 times 0 plus 1 times minus 1. And I can do it for the second row, second column, 0 times 1 plus 1 times 0 is 0, which is the same as I got by doing my 2 vector transformations of the basis vectors in turn. So we've discovered how to do the multiplication of 2 matrices together as being the composition of the 2 transformations, doing the first transformation and then the second. So we can use that to do any type of transformation we want, of some combination of rotations and shears and scales. Now there's one last thing to note, which is we need to ask ourselves the question of, is doing A2 to R and then A1 the same as doing A1 and then A2? That is, can we reverse the order in which I do my matrix multiplication? Well, if I do A2 first, I get this. And then if I rotate those down by 90 degrees, if I rotate this guy down by 90 degrees, he's going to come down like that. He's going to come down to minus 1, 0. And if I rotate this guy down by 90 degrees, he's going to come down like that. So he's going to become 1 on the x and minus 1 on the y. So A2, A1 is going to be minus 1, 0, 1, minus 1. And A1 first, followed by A2, we said was given by this minus 1, minus 1, and this guy 1, 0. And those 2 things, this guy here and this guy here, aren't the same. And you can see this space here, this gives me a parallelogram here, and this one here gives me something altogether different. So these, there is an order dependence to the way in which I do the matrix operations. So it matters whether I rotate then stretch, then shear, or whether I shear then rotate. They're just not the same things. So we have to be very careful with matrix multiplication. We can do A1R and then apply A2, or we can do A2, A1 and then apply it to R. But we can't exchange the order the matrices are in when we multiply it out. So, in summary, what have we said here? there seems to be some kind of deep connection between simultaneous equations, these things called matrices, these guys, and the vectors we were talking about in the last module. And it turns out that solving simultaneous equation problems is appreciating how vectors are transformed by matrices, and that's the heart of linear algebra. So now we're finally going to find a way to solve the apples and bananas problem. And along the way, we're going to find out about a thing called the inverse of a matrix and a method for finding it. So let's go back to that apples and bananas problem. We said that I walked into a shop and I bought 2 apples and 3 bananas, and that cost $8 or euros or whatever my currency is. Then I went into the shop on another day and I buy 10 apples and 1 banana, and I got charged 13 euros for that. So I wrote that down as a matrix times a vector. And I could call that matrix A, and I could call this vector R, and I could call that its output vector S. So A operates on R and gives me S. And what I want to do is I want to find out what R is, what this vector AB is, in order to give me the right numbers for the output vector. Now, let's just think about this matrix A for a moment. Let's see if I can think of another matrix. I'm going to call this matrix A to the minus 1, that when I multiply it by A gives me the identity matrix. And I call this matrix here the inverse of A. Because what it does to A is it exactly reverses whatever A does and gives me just the identity. So if I take this equation, AR equals S, if I multiply it on the left by A to the minus 1 on both sides, well, what I find is that this is just going to be the identity, which is the matrix that does nothing. So when I multiply the identity by R, I just get R. So then I've got R is equal to A to the minus 1 times S, the inverse matrix of A times S. So if I could find the inverse of A, the matrix when multiplied by A that gives me the inverse, if I can find the inverse of A, I can solve my problem, and I can find what my A and B are, and I've solved my apples and bananas problem. Now, hold that thought about inverses for just a moment. So we said the inverse of A times A was the identity matrix. And we'll just park that up there for a moment. Now, I actually don't have to go all the way to the inverse to solve the apples and bananas problem. I can do it just by substitutions. So let's look at a slightly more complicated problem and see what I mean. So I'm going to take a matrix that looks like this. 1, 1, 3, 1, 2, 4, 1, 1, 2. And I'm going to say that I have apples and bananas and carrots, say. Okay, they're not a fruit, but they're another sort of fruit-like object that we eat. And so I'm saying that I bought 1 apple, 1 banana, and 3 carrots, and that cost me, let's say, 15 euros. Another day I went in, I bought 1, 2, and 4, and that cost me 21 euros. And another day I bought 1, 1, and 2, and that cost me 13 euros. Now, the thing to notice about a system of equations like this is that I can, if I take this row off of another row, I haven't changed anything, right? So I know that an apple, a banana, and 3 carrots costs 15. So if I take an apple, a banana, and 3 carrots and 15 off of the next row, I haven't changed anything really about that row. The same for the third row. So I can make this problem simpler by going and doing that. That's sort of a process of elimination. So if I take, if I call this row 1, row 2, and row 3, if I take row 1 off of row 2, then I would have, take row 1 off of row 2, I'll have 0, 1, 1. If I take row 1 off of row 3, I'll have 0, 0, and minus 1. I'd still have A, B, and C. And I've taken, on the right-hand side, I've taken row 1. I've taken row 1 off of row 2, so I've taken 15 off of 21, so I'll have 6 left. And I've taken row 1 off of row 3, so I'll have 15 minus 13 is 13 minus 15 is minus 2. So, interesting. So now I can see that actually minus C is equal to minus 2. So I can multiply that row through by minus 1 here. I'll just change pens. And I've got a solution now for C, that C is equal to 2. So that's interesting. Now, I've got what it's called a triangular matrix. That is, everything below the body diagonal is 0. And that's a very interesting sort of matrix. I've reduced it to what's called echelon form. All the numbers below the leading diagonal are 0. Now, I can do what's called back substitution. I can take my answer for C here, and I can put my answer for C back into the first 2 rows. So if I take 1C equals 2, I know that 1 times C here is 2 here, so I can take that off there. And I can do the same. I can take 3 times that off of the first row. So if I take 3 times it off the first row, I'm going to get 1, 1, 0, A, B, C. And I've taken 3 times the first row off of here, so I've taken 3 2s off of here, so I'm going to get 9. If I take that third row off of the second row, I'm going to get 0, 1, 0. And I've got 2 off of 6 is 4. And I can complete, I haven't changed the last row at all. So now I know that C here is equal to 2. I know that if I multiply that row by that column, I've got just B is equal to 4. And I've got A plus B is equal to 9. But I can take my answer for B back off this first row. So I've got then 1, 0, 0, 0, 1, 0, 0, 0, 1. A, B, C. And I've taken 1B, I've taken 4 off of the first row, so that's 5, 4, 2. So my solution here for my apples, bananas and carrots problem is that apples cost €5, bananas cost €4, and carrots cost €2. And that's solved the problem for me. Very nice. So I didn't really have to compute the inverse at all. But I've only found out the answer for this specific set of, this specific output vector. So we said that this was A times R is equal to S. I've only found it for this specific S. If I did the inverse in a general case, I could do it for any S. I could find R for any S. So what I've done here is I've done what's first elimination. I've taken multiples of rows and I've taken them off of each other to get to having a triangular form where the bottom corner here is 0s, and I've just got 1s on the leading diagonal. And then I've done back substitution. Back substitution. Well, I've gone back up of putting the numbers for C back into the first 2 rows, the number for B back into the first row, and so on, to get my solution to my problem. And that's very nice. This is actually one of the most computationally efficient ways to solve this problem. And it's going to work every time, and it's very simple to understand. We can do it in relatively few operations, so it's really, really nice. And one thing to notice here is that in doing so, what I've done is I've transformed A into the identity matrix here. This is just the identity matrix. This 1's on the leading diagonals and 0's everywhere else. So this is going to be a key to a way to find the inverse, which is what we'll look at next. Now, let's think about how I can apply this idea of elimination to find the inverse matrix, which solves the more general problem, no matter what vector I write down on the right-hand side. So I have a 3 by 3 matrix A and its inverse B, which are multiplied together to give the identity matrix I. So before we had the matrix for A was 1, 1, 3, 1, 2, 4, and 1, 1, 2. And B here is I'm going to actually introduce some notation. I'm going to call B composed of elements B11, B12, B13, where the first digit represents the row. So then I'll have B21. The second digit represents the column. So this would then be B22, and this one would be B row 2, column 3. I'll have B31, B32, B33. So that's the row, and that's the column. Equals I. And what we're saying here is that B is actually the inverse of A. So that is, if I multiply A by its inverse, I'll get the identity. And actually the inverse is special because I can do it either way around. I can apply it to A on the right or on the left and it'll still work. Because I times the inverse of A is just the inverse of A, so it doesn't really matter which way round I do it. But I'm just doing it here so that I've got some B's to play with and I don't get confused between my A's and my B's. Right? But for this example, I'm saying B is the inverse matrix of A. Now, notice that this first column of B here is just a vector. It's a vector that describes what the B matrix, the inverse of A, does to space. Actually, it's the transformation that that vector does to the the x-axis, if you like. So, and the identity matrix is just 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So I could write this down. I could write down this A, that big square guy, times B11, B21, B31, and I would get just the first column of the identity matrix, 1, 0, 0. Now, I could solve that by my elimination method and back substitution, just in the way I did before, except I'd be juggling different numbers here. Then I could do it again for the second column of B, the second vector of B, for the second vector of the identity matrix. And I could do it again for the third one. So I'd be doing that in some series, if you like. But, here's the fun bit, I could do it all at once. So I'm going to do this process of elimination and back substitution all at once. I'm going to do it for all the columns on the right-hand side simultaneously. So if I take the first row here and I take it off the second row, as before, I'm going to get rid of this one. And if I take the first row off of the third row, I'm going to get rid of both this one and this one. So if I've got, put the unaltered ones down here, 1, 1, 3. If I take that off of the second row, I'm going to get 0, 1, 1. And if I take that off the third row, I'm going to get 0, 0, minus 1. So on the right-hand side, I'm going to have the unaltered one is 1, 0, 0. And I've taken that off of the second row. So I've got taken 1 off that. That's minus 1, 1, 0. And I've taken that off of the third row as well. So I've got minus 1, 0, 1. And so now I can multiply that third row through by minus 1, and that's in the form I then want. Well, I've got 1s on the leading diagonal and 0s below it. So when I multiply that through by minus 1, I get a plus there and a minus there. Now I can substitute that third row back into the second and first rows. So I can take one of it off of the second row, and I can take 3 of it off of the first row. So now the unaltered one is the bottom one, 1, 0, minus 1. If I take one of those off of the second row, then I've got 0, 1, 0 there. I'm going to take that off of the second row over here. So if I take 1 off of minus 1, I get minus 2. Take 0 off 1, I've got 1. Take minus 1 off of 0, I'm effectively adding 1. Then I want to do that again to the first row. I want to take 3 of them off to make this guy here 0. So I've got then 1, 1, 0 there. And I want to take 3 of these off of the first row. So I take 3 off of 1, gives me minus 2. Take 0 off there. And I've got to take 3 of minus 1 off of 0, so that gives me plus 3. So we're nearly there. I've just got this irritating one here. I've got to take this row off of this row, and I'll be home. So if I take my third row is unaltered. Let's put some brackets in. My third row is unaltered. My second row is going to be unaltered. 1, 0, minus 1, minus 2, 1, 1. If I take that row off of that row, then that altered one gives me 1, 0, 0. Take the 1 off there. Take this row off of this row, minus 2 off of minus 2. I've got to take minus 2 off of minus 2, so that gives me 0. Got to take 1 off of 0, that gives me minus 1. And I've got to take 1 off of 3, which gives me 2. So that's my answer. So now I've got the identity matrix here for A, in effect. I've transformed A till it's the identity matrix. I've got my B matrix, which I haven't really changed. and my identity matrix over here I've changed. So now I've got an identity times a B matrix is equal to this guy. So the identity times something is just itself. So this is, in fact, my answer for the inverse of A, or B. So I've found a way here to find the inverse of a matrix just by doing my row elimination and then my back substitution, which is really cool. So what we've done is we've found an inverse matrix, A to the minus 1 here, and if we multiply A times A to the minus 1, we'll get the identity. And prove to yourself, if you like, just pause for a moment and have a go at doing that for yourself and verify that that times that does in fact give you the identity matrix. And in school you probably did this a different way, but computationally this way is much easier, particularly when you come to higher dimensions, 100 rows and columns or something like that. There are a computationally faster method of doing what's called a decomposition process. And in practice, what you do in any program that you write is you simply call the solver for your problem, or the function, something like inv A, or whatever it is, and it will pick the best method by inspecting the matrix you give it and return the answer. But the point here is to show how these problems are actually solved in a computer, and also we'll observe some of the properties of these methods in different circumstances that will affect the sorts of things we want to do when solving these sorts of problems. So what we've done here is figured out how to solve both sets of linear equations in the general case by a procedure we can implement in a computer really easily. And we've made that general by finding a general method to find the inverse of a matrix in the general case for whatever is on the right-hand side of our system of equations. And hopefully that's really satisfying and really nice. In the final video in this module, we're going to look at a property of a matrix called the determinant. And we'll also look at what happens when the matrix doesn't have linearly independent basis vectors. If you remember the basis vectors that we looked at in the last module. Let's go back and look at a simple matrix like this guy here, A0, 0, D. What this matrix is going to do to the space, if I've got my original basis vectors, and we called them E1 hat was 1, 0, and we called this guy E2 hat was 0, 1. If I multiply this by E1 hat, I get the new version of E1 in the new vector space, which will just be E1 prime, the new one, and that'll be A0. So what I've done is I've stretched this guy out by a factor of A. And in the other direction, I'll get a new vector, let's call him E2 prime, which is 0D. So what I've done to the space, I've taken every bit of grid in the space that was of area 1, and I've made it A times bigger this way, and I've made it D times bigger that way. So I've changed the area of the grid cells of the space by a factor of AD. And this AD I call the determinant. Now, if I instead have a matrix which is A0, BD, what this is going to do is it's still going to stretch E1 out, E1 hat, my unit vector, still going to stretch it out by a factor of A, but on the other axis, I'm going to move E2 hat to BD. I'm going to move it over to some place where E2 prime is equal to BD. So what I've done then is I've taken my original grid here, and I've, as well as stretching it out by A and up by D, I've also sheared it over by B. But this area here is just the base times the perpendicular height, and its perpendicular height's D, so the area here is still AD, so the determinant is still AD. I've still changed the size of the space, the scale of the space, which is what the determinant is, by a factor of AD. But if I have a general matrix A, C, B, D, then what that's going to do to the space, to my original axis vectors, is it's going to turn that into something like this. The first one's going to do something like that, say, and the second one's going to do something like that, say. And so my new area is going to be that. And if I want to find that area, I have to do a little bit of maths. So I've done the bit of maths, and here it is. Here's what I've done is I've found the area of this parallelogram by finding the area of the whole box here and taking off all the little bits around it, and I find that the area is AD minus BC. Pause for a moment if you like and verify that that's correct. And I'm going to denote, if this is the matrix A, I'm going to denote that this area, this determinant, is with vertical lines here, and that's then saying the determinant of A for a 2 by 2 matrix is just AD minus BC. Now, in school when you looked at matrices, you probably saw that you could find the inverse in the following way. If you've got a matrix A, B, C, D, then you probably said that you could find the inverse by multiplying by a matrix where you exchange the A and the D, and you took a minus sign on the B and the C, on the off-diagonal terms. And you also multiplied by another number. But let's just multiply that out and see what we get. So when we multiply that out, we're going to get, multiply that row by that column, we'll get AD minus BC. Interesting. And we'll get A times minus B, so minus AB, plus AB. So that's 0. Here we'll get CD minus CD, so that's 0. And when we multiply that row by that column, we'll get minus BC plus AD. So that's AD minus BC again. Now, if I divide that through by a number AD minus BC, if I divide by the determinant, I'll divide this through by AD minus BC, and these will turn into 1. So now I've got the identity matrix, and this guy times the determinant is in fact the inverse of the 2 by 2 matrix. And that was how you would have done it by school. And this is the determinant here, and that's really what the determinant is. It's the amount that the original matrix stretched out space. And by dividing by the determinant, we're normalizing the space back to its original size. That's what that determinant bit does. Now, we could spend another video looking at an extension of the idea of elimination and back substitution of that row echelon idea to find out how to find determinants computationally. But this is both tricky to show and derive, and it's kind of pointless. Knowing how to do the operations isn't a useful skill anymore, because we just type det A into our computer. Thus, I just type det A, and my computer gives me the answer. Done. From a learning perspective, it doesn't add much. Row echelon does, which is why we went through it. So I'm not going to teach you how to do determinants. If you want to know, then look up QR decomposition online, or better yet, look in a linear algebra textbook. Now, let's think about this matrix. Let's think about a matrix A, which is 1, 1, 2, 2. What this guy does is he takes space, and he makes our first basis vector here into 1, 1. It makes him go there, up to 1, 1. And makes our second basis vector go to this one here, go to 2, 2. So what he's done is he's taken a space with areas and he's collapsed everything onto a line. All of my y's here are going to collapse onto this line. All my x's are going to collapse onto this line. So he's reduced the dimensionality of the space. All of the space is going to end up, every point in space is going to map onto some point on this line here. Now, notice that the determinant of this matrix is going to be 0. It doesn't, the area enclosed by the new basis vectors is 0. And if I do AD minus BC, I've got 1 times 2 minus 1 times 2. So the determinant of A is 1 times 2 minus 1 times 2 is 0. So graphically, we can see that it's 0, and we can compute that it's 0. If I had a 3 by 3 matrix describing a 3D space, then that linear dependence of one of the new basis vectors on the other two would mean that the new space was either a plane, or if there was only one independent basis vector, it would be a line. In either case, the volume enclosed would be 0, so the determinant would be 0. Now, let's turn back to our row echelon form. Let's take this set of simultaneous equations here. Let's take 1, 1, 2, 1, 2, 3, and 3, 4, 7 times ABC, some vector, is equal to 12, 17, 29. Now, you'll notice here that if I take the sum of the first two rows, I get the third row. So that is row 1 plus row 2 is equal to row 3. And also if I take the columns, if I take 2 times column 1 plus 1 times column 2, then I'll get 2 plus 1 is 3, 2 plus 2 is 4, 4 plus 3 is 7. So that's equal to column 3. So if I think of these as the new basis vectors of my matrix, then they're not linearly independent. This one guy is a linear combination of these two. It's twice this one plus 1 times the middle one. So this is going to be a problem. It's going to be a thing that collapses my vector space from being 3D to 2D. It's going to collapse every point in space onto a plane. And that's going to be tricky. Let's see how. So when I try and reduce this to row echelon form, if I take the first row, 1, 1, 3, ABC equals 12. If I take that off the second row, then I'm going to get a 0. Take the first row off the second, I'm going to get 0 there. Then I'm going to take 1 off there, I'm going to have 1. Take 3 off there, I'm going to have 1. Take 12 off 17, I'll have 5. And if I take row 1 and row 2 off of row 3, then I'm going to get 0, 0, 0 along the bottom row. And if I take 12 and 17 off 29, I'm going to get 0 as well. So, this is row echelon form, but I don't have a 1 here. So I find that I'm now getting 0c equals 0. And that's true, but it's not very useful. I don't have a solution for c. So now I can't back substitute. I can't solve my system of equations anymore. I don't have enough information. If you think, when I went into the shop, what my mistake was, when I went in to buy apples and bananas and carrots the third time, I ordered just a copy of my first two orders, the sum of my first two orders. So I didn't get any new information. I just found out that the cost of my first two orders combined was 29. And so I don't have enough data to find out the solution for how much apples and bananas and carrots cost. My third order wasn't linearly independent from my first two in sort of matrices and vectors language. So we've shown that where the basis vectors describing the matrix aren't linearly independent, then the determinant is 0, and I can't solve the system. That is, because these aren't linearly independent, I don't have a determinant with any volume. It's now collapsed to a plane, so the determinant's 0, and that means when I try my row echelon form, I can't solve the problem. And that means I can't invert the matrix, which means I'm stuck. So in fact, this matrix has no inverse. It's what's called singular. So there are situations where I might want to do a transformation that collapses the number of dimensions in a space. I might want to do that sometimes, but that will come at a cost. Another way of looking at this is that the inverse matrix lets me undo my transformation. It lets me get from the new vectors back to the original vectors. But if I've dumped a dimension, if I've scrapped a dimension by turning 2D space into a line or 3D space into a plane or a line, I can't undo that anymore. I don't have enough information because I've lost some of it in doing the transformation. I've lost that third dimension. So in general, it's worth checking before you propose a new basis vector set and then use a matrix to transform your data vectors, that this is a transformation you can undo. And you do that by checking that your proposed new basis vectors are linearly independent. Now, There's an important other way to write matrix transformations down, which is called the Einstein summation convention. And that writes down what the actual operations are on the elements of a matrix, which is useful when you're coding or programming. It also lets us see something neat about the dot product that I want to show you, and it lets us deal with non-square matrices. When we started, we said that multiplying a matrix by a vector, or with another matrix, is a process of taking every element in each row in turn, multiplying it with a corresponding element in each column in the other matrix, and adding them all up and putting them in place. So let's write that down just to make that concrete. So I'm going to write down a matrix A here, and I'm going to give it elements. A is an n by n matrix, and I'm going to give it elements A11, A21, all the way down to AN1, and then A12 all the way across to A1n, and then I'll have A22 here all the way across, all the way down, until I fill it all in, and I've got ANN down here. So the first suffix on this matrix, or first suffix on all of these elements in the matrix, is the row number, and the second one is the column number. Now, if I want to multiply A by another matrix B, and that's also going to be an n by n matrix, and that'll have elements B11, B12 across to B1n, and down to Bn1 and across to Bnn. Dot, 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 dot. If I multiply this together, I'm going to get another matrix, which I'll call AB. And then what I'm going to do is I'm going to take a row of A, multiply it by the elements of a column of B, and put those in the corresponding place. So let's do an example. So if I want element, let's say AB, element 2, 3, I'm going to get that by taking row 2 of A, multiplied by column 3 of B. So I'm going to take row 2 of A, that's going to be A21, A22, and all the others up to A2n. And I'm going to multiply it by column 3 of B, so that's B13, B23, all the way to Bn3. And I'm going to add all those up. And I'll have a dot, dot, dot in between. So that's going to be this element, row 2, column 3 of AB. Now, in Einstein's convention, what you do is you say, well, okay, this is the sum over some elements j of Aij, Bj, k, where, so if I add these up over all the possible j's, I'm going to get A11, B11 plus A12, B21, and so on, and that's for I and k is 1. And I'm going to then go around all the possible i's and k's. So what Einstein then says is he then says, well, okay, if I've got a repeated index, I just won't bother with the sum, and I'll just write that down as being Aij, Bjk, and that's equal to this, the product ABIK. So ABIK is equal to AI1B1K plus AI2B2K plus I3B3K, and so on, until you've done all the possible J's. And then you do that for all the possible i's and k's, and that will give you your whole matrix for AB for the product. Now this is quite nice. If you were coding, you just run 3 loops over I, j, and k, and then use an accumulator on the j's here to find the elements of the product matrix AB. So the summation convention gives you a quick way of coding up these sorts of operations. Now, we haven't talked about this so far, but now we can see it. There's no reason, so long as the matrices have the same number of entries in J, that we can't multiply them together, even if they're not the same shape. So we could multiply a 2 by 3 matrix, something with 2 rows and 3 columns, so 1, 2, 3, 1, 2, 3, by a 3 by 4 matrix, 3 there and 4 there, so it's got 1, 2, 3, 4 times. And when I multiply those together, I'm going to go that row times that column. I've got the same number of j's in each case. So, and then I'm going to be able to do that for all of the possible columns. So I'm going to get something with 4 columns. And when I'm going to be able to do that for the 2 rows here, I'm going to be able to do that row times that one. So I'm going to get a 2 by 4 matrix out. So it's going to have 1, 2, 3, 4, 1, 2, 3, 4. So I can multiply together these non-square matrices if I want to, and I'll get, in a general case, some other non-square matrix. I'm going to have the number of rows of the one on the left and the number of columns of the one on the right. Now, all sorts of matrix properties that you might want, inverses and so on, determinants, all start to get messy and mucky, and you sometimes can't even compute them when you're doing this sort of thing. But there are times when you want to do it. And the Einstein summation convention makes it very easy to see how you do it and how it's going to work. As long as you've got the same number of j's, you're good. You can multiply them together. Now, let's revisit the dot product in light of the summation convention. So if we've got 2 vectors, let's call them u and v. And we'll say u's a column vector having elements ui, and v's another column vector having elements vi. And when we dot them together, what we're doing is we're multiplying u1 by v1, adding u2, v2 all the way up. So in the summation convention, that's just ui, vi, where we repeat over all the i's and add. But this is just like writing U as a row matrix, pushing U over from being a vector to being a matrix with elements U1, U2, all the way up to UN, and multiplying it by another matrix, V1, V2, all the way up to Vn. That's the same. That matrix multiplication is the same thing as the dot product. I just push the U vector over, and then my dot product is just like doing a matrix multiplication, which is sort of neat. So there's some equivalence between a matrix transformation, a matrix multiplication, and the dot product. So let's look at that. Now, if I take a unit vector here, let's call him u hat, with components u1 and u2. And let's imagine what happens if I dot him with the axis vectors. So if I've got an axis here, E1 hat, which would be 1, 0, and I've got another axis here, E2 hat, which will be 0, 1. Now let's think about what happens when I dot U hat with E1, when I do the projection of U hat onto E1. So when I drop U hat down onto the axis here, when I do the projection of U hat onto E1, I'm going to get a length here just of U1, just of the x-axis element of U hat. Now what happens if I drop, project E1 onto U hat? Well, I'm then going to get this projection, and I'm going to get a length here, this projected length here. Now, the fun thing is, we can actually draw a line of symmetry here through these two projections where they cross. And this little triangle and this little triangle are actually the same. You can go and do a bit of geometry and prove to yourself that that's true. So this length here, this projection, there, that projection, is the same length as that projection, which is implied by the dot product. If I dot E1 with U hat, when I do this multiplication here, it's symmetric. I can flip them around and I get the same answer. So this shows geometrically why that's true. And if we repeat this with the other axes, with E2 here and any other axes there are, then we'll also get the same results. So this is why the projection is symmetric and the dot product is symmetric, and why projection is the dot product. So there's this connection between this numerical thing, matrix multiplication, and this geometric thing, projection, which is quite beautiful and mind-blowing, really. And that's why we talk about a matrix multiplication with a vector as being the projection of that vector onto the vectors composing the matrix, the columns of the matrix. So what we've done in this video is look at the summation convention, which is a compact and computationally useful but not very visual way to write down matrix operations. And that's opened up looking at funny shaped matrices, and that's opened up re-examining the dot product here. So that's really nice. We've said before that the columns of a transformation matrix are the axes of the new basis vectors of the mapping in my coordinate system. We're now going to spend a little while looking at how to transform a vector from one set of basis vectors to another. Let's say I have two new basis vectors that describe the world of Panda Bear here, and Panda's world is orange. So Panda's got first a basis vector there, and then another basis vector there, say. And let's say in my world, Panda Bear's basis vectors are at 3, 1 and are at 1, 1. And my basis vectors here are E1 hat equals 0, 1 for E2 hat, and E1 hat is equal to 1, 0. So those are my basis vectors, and the orange ones are Panda's basis vectors. Now, and so Panda's basis vectors, the first one for Panda is his 1, 0, and the second one is 0, 1 in Panda's world. So Bear's basis vectors are 3, 1 and 1, 1 in my blue frame. That is, I can write down Bear's transformation matrix as 3, 1, 1, 1. Now, let's take some vector I want to transform. Let's say that vector is, in Bear's world, is the vector a half of 3, 1 in Bear's world. So it's 3 over 2, 1 over 2. So the instruction there is do 3 over 2 of 3, 1, and then do 1 over 2, a half of 1, 1, in my frame, if you like. So in my world, that's going to give me the answer of 3 times 3 over 2 plus 1 times 1 over 2 is 9, 10 halves, which is 5. And 1 times 3 over 2 plus 1 times a half, so that's a total of 2. So that's the vector 5, 2 in my world. 5, 2. Those two are the same things. So this is Bear's vector, and this is my vector. So this transformation matrix here are Bear's basis in my coordinates, in my coordinate system. So that transforms Bear's vectors into my world, which is a bit of a problem. You know, usually I'd want to translate my world into Bear's world. So we need to figure out how to go the other way. So my next question is, how do I perform that reverse process? Well, it's going to involve the inverse. So if I call Bear's transformation matrix B, I'm going to want B inverse, which is B to the minus 1. And the inverse of this matrix, well, it's actually pretty easy. We can write down the inverse of that matrix pretty easily. It's going to be a half of 1, 3, flip the elements on the leading diagonal, and put a minus on the off-diagonal terms. And we can see the determinant of that's 3 minus 1 is 2, so we divide by the determinant as a half. So that's going to be B to the minus 1. And that's the my basis vectors in Bear's coordinates. So that's my basis in Bear's world. So my 1, 0 is going to be a half of 1 minus 1 in Bear's system, and my 0, 1 is going to be a half of minus 1, 3 in Bear's system. And we can verify that this is true if we take this guy, a half 1 minus 1, and compose it with Bear's vectors. We've got 1 plus minus 1 of those is going to give me 3 plus 1 is 3 minus 1 is 2, 1 minus 1 is 0, so that's 2, 0, halve it, gives you 1, 0. So that really does work. If I take a half 1 minus 1 of Bear's vectors, I get my unit vector. Okay, so that really does do the reverse thing. So then if I take my vector, which was 5, 2, and then I do that sum, I should get the world in Bayes' basis. So I've got 5 times a half minus a half, using that guy, plus 2 times minus 1, 3, and that will give me a half of 3, 2, when I multiply it all out. And if I do the same thing here, I've got 5 times 1, minus 1 times 2, gives me 3 over 2, gives me 3 over 2. It all works out. If you do it that way, or if you do it that way, you still get that answer. So that's Bayes' vector, again, which is the vector we started out with. So that's how you do the reverse process. You need to, if you want to take Bayes' vector into my world, you need Bayes' basis in my coordinate frame. And if you want to do the reverse process, you want my basis in Bayes' coordinate frame. That's probably quite counterintuitive. So let's try another example where this time Bayes' world is going to be an orthonormal basis vector set. So here's our basis vectors at 1, 0, and 0, 1 in my world in blue. And Bayes' world is in orange. Bayes' world has 1, 1 times, and I've made it unit length, so it's 1 over root 2, and minus 1, 1. Again, the unit lengths are 1 over root 2, so they're those two. And those you can do a dot product and verify that those two are at 90 degrees to each other. And they're Bayes' vectors 1, 0, and 0, 1. So then I can write down Bayes' transformation matrix that transforms a vector of Bayes. Now, if I've got the vector in Bayes' world that's 2, 1, then I can write that down. And I will therefore get the vector in my world. So when I multiply that out, what I get is I'll get 1 over root 2 times 2 minus 1, which is 1. And then 1 times 2 plus 1 times 1 gives me 3. So in my world, the vector is, as I've written down, 1 over root 2 times 1, 3. So if I want to do the reverse transformation, I need b to the minus 1. And b to the minus 1 is actually quite easy. Because this is an orthonormal basis, the determinant of this matrix is 1. So it all becomes quite easy. So I just get 1 over root 2, keep the leading terms the same, flip the sign of the off-diagonal terms because it's a 2 by 2 matrix. That's really simple. And if you go and put that in, if you say, if I take 1 over root 2 times 1 minus 1, so I take one of those plus one of those, multiplied by root 2, I do in fact get 1, 0, and the same for 0, 1. It all works. So then if I take the vector in my world, this vector in my world, which is 1, 3, and multiply it out, then what I get is the vector in Bayes' world. So that's 1 plus 3, which is 4, minus 1 plus 3 is 2. And I've got 1 over root 2 times 1 over root 2, so that's a half. So in Bayes' world, this vector is 2, 1, which is what we originally said. So it really works. Now this was all prep, really, for the fun part, which is, we said before in the vectors module that we could do this just by using projections if the new basis vectors were orthogonal, which these are. So let's see how this works with projections. So let's try it with projections. What we said before was that if I take my version of the vector and dot it with Bayes' axis, so the first of Bayes' axes is that in my world, then I will get the answer of the vector in Bayes' world. So that gives me 1 over root 2 times 1 over root 2, which is a half, of 1 plus 3, which is 4. So that gives me 2. And that's going to be the first component of Bayes' vector because it's the first of Bayes' axes. And I can do it again with the other of Bayes' axes. So that's 1 over root 2, 1, 3. That's the vector in my world, with the other of Bayes' axes, which is 1 over root 2 times minus 1, 1. And when I do that dot product, what I'll get, 1 over root 2's will multiply to give me a half again, and I've got 1 times minus 1 plus 3 times 1 is a total of 2, which is 1. And that's Bayes' vector, notice, 2, 1. So I've used projections here to translate my vector to Bayes' vector just using the dot product. Now remember, with the vector product, what I'd have to do is I'd have to remember to normalise when I did the multiplication by Bayes' vectors. I'd have to normalise by their lengths, but in this case their lengths are 1. So it's actually really easy. So we don't have to do the complicated matrix maths. We can just use the dot product if Bayes' vectors are orthogonal. Now there is one last thing. If you try this with the example we did before, with Bayes' vectors of 3, 1 and 1, 1, so before we had those being Bayes' vectors, if you try the dot product with those, because they're not orthogonal to each other, it won't work. And give it a go for yourself and verify that it really won't work, that they need to be orthogonal for this to work. If you have them not being orthogonal, you can still do it with the matrix transformation, you just can't do it with the dot product. Now, let's do one last thing. For this example, let's go back to the first transformation of Bayes, the first set of Bayes axes, which were 3, 1 was his first axis, and 1, 1 was his second axis. And we said that was the matrix B, which described Bayes' basis in my world. Now, let's say I have a vector which I want to do something to. Yeah, I want to rotate it or shift it or transform it or send it somewhere. Right? And I only know that vector in Bayes' world. Right? So relative to Bayes' coordinate system. And we'll call that vector xy in Bayes' world. Now my problem is I don't know what this transformation, a rotation say, it could be a reflection, whatever it is. I don't know what that transformation matrix is in Bayes' funny coordinate system. I only know it in my nice sensible coordinate system because Bayes' crazy, right? He has these crazy non-orthogonal, non-unit vectors that he's using to describe his axes. And I only know the transformation in my system. So the first thing I'm going to do, actually, is I'm going to take Bayes' vector and I'm going to put it in my world. And then I can apply the rotation in my world. So first I'm going to do this multiplication, and that gives me the vector in my world, right? That's nice. Then what I'm going to do is I'm going to do this rotation. So let's call this rotation R, and we'll say that in my world, I know that that rotation is 1 over root 2 times 1 minus 1, 1, 1. What that does is that it actually rotates. If I imagine if I've got some basis vectors like that, it turns them to 1, 1, goes over there, and that one goes to, this one goes to minus 1, 1, so they both get rotated. So this is a rotation actually of 45 degrees. So then I've got my vector. When I multiply it by r, which is my 45 degree rotation, I've then got the vector rotated and in my description, in my basis. So then, how do I get a vector in my basis back into Bayes' basis? Because Bayer doesn't care. Bayer isn't interested in my basis. He's interested in what this rotation is and what the vector is when it's rotated in his basis. Because he only really wants to know about his coordinate system because, you know, he's a bear with little brain. So I need to then turn it back into a vector in Bayes' basis. So I'm then going to have to use b to the minus 1, which is the thing that does that. And that is the vector 3, 1, leave the 1s on the leading diagonal, flip the sign of the other 2. It's easy for 2 by 2. And the determinant of that is 3 minus 1. So I've got to divide by the determinant of 2. So that, when I do that whole set, I've then got the vector back in Bayes' basis after the rotation. In Bayes' basis. So I figured out how to do this rotation in Bayes' world. So if I multiply those three out, then I just get what that rotation matrix is in Bear's coordinate system. So now let's just do the sums in order just to make ourselves happy that we can all do this. So I've got 1 times 3 plus minus 1 times 1, so I've got 2. And then if I do this one, I've got 1 times 1 minus 1 times 1, so I've got 0. Then I've got 1 times 3 plus 1 times 1, I've got 4. And I've got 1 times 1 plus 1 times 1 is going to give me 2. And I've all got to keep my 1 over root 2 in there. So that's what RB is. Then if I do b to the minus 1 times RB, I've got to multiply that guy by that guy, and I get it back in Bear's basis. So then I've got to do that, so I've got 3 times 2 minus 4 is 6 minus 4 gives me 2, divided by 2 gives me minus 1. So 3 times 2 is 6, minus 4 is minus 2, divided by 2 is minus 1. Then I do it again, and as I go through, I will get the answer, which I will just write out for you, which is 1 over root 2 times minus 1, 5, 3. So that's what a 45-degree rotation looks like in Bear's coordinate system. And notice that it's completely different to the one in my standard basis. And isn't very easy necessarily or obvious to intuit just from your head. You have to do the calculation. So if you want to do some kind of transformation but in some funny basis, this equation, b to the minus 1 times r times b, is going to be very useful. So to step back here, the point here is that when we transform to non-orthonormal coordinate systems, then the transformation matrices also change, and we have to be mindful of that. And this sort of algebra you see all the time. We've got the transformation matrix R and B inverse B wrapping around it to do the translation from my world into the world of the new basis system. So thanks, Bear. That was really useful. So what we've done in this video is we've looked at how the numbers in the matrix we use to describe a vector change when we change the basis. And we've thought about coordinate systems. It's a bit counterintuitive, but Bear helped us out. We also saw that if we have an orthonormal basis, then we can just use the dot product to do the projections like we said before. And we also saw that if we use an arbitrary basis, then the transformations themselves will change. It's going to be really useful if we can make a transformation matrix whose column vectors make up a new basis, all of whose component vectors are perpendicular or what's called orthogonal to each other. In this video, we're going to look at how we do this and why it's useful. First, I want to define a new operation on a matrix that we haven't seen before called the transpose. This is where we interchange all of the elements of the rows and columns of our matrix A. If I've got a matrix A with elements ij, I'm going to say the transpose of it is where I interchange all of those i's and j's. So if I have a matrix, say 1, 2, 3, 4, if A is that, then A transpose will be where I interchange the elements on all the rows and columns. So the 1, 1, if I interchange it with, will stay where it is. I'll stay being 1. And the 4 will stay being 1. So the ones on the leading diagonal stay where they are. But when I do this, I flip the elements that are not on the leading diagonal. So the 2 and the 3 will swap there. So that's the transpose of A. Now let's imagine I have a matrix A here, who's an n by n matrix, who's got a series of column vectors, which are going to be the basis vectors of the new transformed vector space. And they're, each of which is going to be, so A, I1, A, I2, all the way to A, I, n, because I've got n of those column vectors, each of which has n rows. So that's, if you like, A1, A2, all the way up to AN, those vectors. And I'm going to say two things about those vectors. First, that they're of unit length, so they have little hats, and that they're orthogonal to each other. That is, A1 dot A2 is equal to 0. In fact, AI dot AJ is equal to 0 if I isn't J. And if they're orthogonal to each other and of unit length, it'll be equal to 1 if I equals J. Now, let's say I pre-multiply A by its transpose. What I'll then have is a series of row vectors of all of those individual A hats, but transpose pushed over into being rows. So this will be A1 hat as a row, that'll be A2 hat, all the way down to AN hat. Now what happens when I multiply A transpose by A? Well, what I'll get is I'll get here another matrix, which will also be square, ATA, and I've got that row times that column being the first element, but that's just the dot product of A1 hat with itself, and that's 1, so I get a 1 here. The next element, A1 hat by A2 hat, well, that's 0, and I'm going to get that all the way across. If I do A2 hat times A1 hat, that's also going to be 0 because it's the dot product of two orthogonal vectors. And when I do A2 hat with A2 hat, it's going to be 1 because they're both unit vectors, they're the same. So a matrix dotted with itself gives me 1, and so on and so on. And what I'm going to build up is I'm going to build up a identity matrix where I've got zeros all the way down, zeros all the way down there, and so on. So I've got zeros all the way. And I'm going to just have the identity matrix. So what I've found here is that in the case where A is composed of vectors that are normal to each other and of unit length, when they're orthonormal, that's what that's called, orthonormal, let's write that guy down, orthonormal, that's what that means. They're all of unit length and they are all perpendicular to each other. Then in that case, A transpose times A is the identity. So A transpose is actually the inverse of A. That's really fun. So in the case where I have an orthonormal basis vector set composing A, then the transpose is the inverse. So I don't have to go to all the faff of finding the inverse and doing all of that hard work. I could just write it down immediately just by doing the transpose in a moment. And this is then, A, in that case, is then what's called an orthogonal matrix. One thing also to know about an orthogonal matrix is that because all the basis vectors are of unit length here, it must scale space by a factor of 1. It doesn't make the space any bigger or smaller. So the determinant of an orthogonal matrix must be either plus or minus 1. So we can write that down. The determinant of A is equal to plus or minus 1. The minus 1 arises if the new basis vector set flips space around, that is, if they make it left-handed from the right-handed it was originally. Notice that if AT, A transpose, is the inverse, I should also be able to multiply A by AT and get the inverse. So I could pre or post multiply and still get the identity. And that means by the same logic that the rows of the orthogonal matrix are also orthonormal to each other. And we saw in the last video that actually the inverse is the matrix that does the reverse transformation. So the transpose matrix of an orthogonal basis set is itself another orthogonal basis set, which is really neat. Now, remember that in the last module on vectors, we said that transforming a vector onto a new coordinate system was just taking the projection or dot product of that vector onto each of the new basis vectors as long as they were orthogonal to each other. So if I've got a vector, let's call him R there, and I want to project him into a new set of axes, let's go that one being some E1 and that one being E2. If these are orthogonal to each other, then I can project it into the new vector space we said just by taking the dot product of R with E2 and the dot product of R with E1, and then we'd have its components in the new set of axes. If you want to pause and think about that for a moment, in light of all that we've learned here about matrices, where we could do it all in one go, then just pause and look at this just for a moment. Now, in data science, really what we're saying here is that wherever possible, we want to use an orthonormal basis vector set when we transform our data. That means that A, the transformation matrix, will be an orthogonal matrix, and therefore the transpose will be the inverse, and it will be really easy to compute. It means that the transformation will be reversible, because space doesn't get collapsed by any dimensions. It means the projection's just the dot product. Lots of things are nice and lovely. And if I arrange the basis vectors in the correct order, then the determinant will be 1. An easy way to check if they aren't in the right order is you calculate the determinant and find if it is -1, then you've transformed from right to left-handed. Just exchange a pair of the vectors, and then you will get a determinant of 1, in fact. And you'll still have a right-handed set. It'll still be a little bit nicer and easier. So what we've done in this video is look at the transpose, and that's led us to find out about the most convenient basis vector set of all, the orthonormal basis vector set, which together make the orthogonal matrix, whose inverse is its transpose. We've said several times now that life is much easier if we can construct an orthonormal basis vector set, but we haven't talked about how to do it. So in this video we'll do that, starting from the assumption that we already have some linearly independent vectors that span the space we're interested in. So let's say I have some vectors v, and I've got a whole group of them, v1, v2, all the way up to vn, and there's enough of them that they span the space. So let's sort of sketch them out. So I've got, say, a v1 here, a v2 over here, another v3 down there somewhere. And they're linearly independent. Let's assume that. If you want to check linear independence, you can write down their columns in a matrix and check the determinant isn't 0. If they were linearly dependent, that would give you a 0 determinant. But they aren't orthogonal to each other or of unit length. My life would probably be easier if I could construct some orthonormal basis somehow. And there's a process for doing that, which is called the Gram-Schmidt process. The Gram-Schmidt process, which is what we're going to look at now. Let's take arbitrarily the first vector in my set, call him v1. So we take v1. In this first step, let's call him she actually, she gets to survive unscathed. So we're just going to normalize her, and we're going to say that my eventual first basis vector e is going to be equal to v1 just normalized to be of unit length, just divided by its length. So e is just going to be some normalized version of v1. And I can now think of v2 as being composed of two things. One is a component, and let's do this in orange, a component that's in the direction of e1, like that, plus a component that's perpendicular to e1. And but the component that's in the direction of e1 I can find by taking the vector projection of v2 onto e1. So I can say v2 is equal to the vector projection of v2 onto e1, dotted together. And if I want to get that actually as a vector, I'll have to take e1, which is of unit length. I'd have to divide by the length of e1, but the length of e1 is 1, so you can forget it. And if I take that off of v2, then I'll have this guy, and let's call him u2. So I can then say that u2, so plus u2. So I can then rearrange this and say that u2 is equal to v2 minus this projection, v2.e1 times e1. And if I normalize u2, if I take u2 divided by its length, then I'll have a unit vector which is going to be normal to v1. So if I take a normalized version of that, let's say it's that will be e2. And that will be at 90 degrees to e1, so it'll actually be there, e2, once I've moved it over. And that will be another unit length vector, normal to e1, so that's the first part of taking an orthonormal basis. Now, my third vector, v3, isn't a linear combination of v1 and v2, so v3 isn't in the plane defined by v1 and v2. So it's not in the plane of e1 and e2 either. So I can project v3 down, let's say something like that, onto the plane of E2 and E1, and that projection will be some vector in the plane composed of E2s and E1s. So I can then write down that V3 minus V3 dotted with E1, E1s, that's going to be the component of V3 that's made up of E1s, minus V3 dotted with E2, E2s, that's the component of V3 that's made up of E2s. And then all that's going to be left is going to be this perpendicular guy there. So that's going to be a perpendicular vector, which we'll call U3, which is perpendicular to the plane. Now, it's some funny 3D space, so the diagram gets quite messy. And then if I normalize U3, divide by the length of U3, then I'll have a unit vector which is normal to the plane, normal to the other two. So now I've got an orthonormal basis for E1, E2, E3. And I can keep on going through all the VNs until I've got enough orthonormal basis vectors to complete the set and span the space that I originally had. But I've gone from a bunch of awkward, non-orthogonal, non-unit vectors to a bunch of nice orthogonal unit vectors, an orthonormal basis set. So that's how I construct an orthonormal basis set and make my life easy so that my transformation vectors are nice, my transformation matrices are nice, sorry, and so that I can do the transposes, the inverse, and all those lovely things. So I can use dot product projections for the transformations, all those nice things that are going to make my life very, very much nicer whenever I'm doing any transformations or rotations or whatever it is I want to do with my vectors. So that's going to be really nice. This is a really nice process. And what we'll do next is we'll apply this, we'll try this for an example and see how it rolls, and then apply that to doing a transformation. Okay, so let's put all this together. Let's use our transformations knowledge and our bases knowledge in order to do something quite tricky and see if we can't actually make our life quite simple. What I want to do here is know what a vector looks like when I reflect it in some funny plane. For example, the way this board works, when I write on the light board here, if you're looking at it, all the writing would appear mirrored. But what we do to make that work is we reflect everything in post-production, left, right, and then everything comes out okay. The example we're going to do here asks what the reflection of Bear, say, something in a mirror, would look like to me if the mirror was off at some funny angle. Now, my first challenge is going to be that I don't know the plane of the mirror very well. But I do know two vectors in the mirror, 1, 1, 1, and 2, 0, 1. And I've got a third vector, which is out of the plane of the mirror, which is at 3, 1, minus 1. That's my third vector. So I've got vectors v1, v2, and v3. And these two guys are in the plane of the mirror. We could draw it something like v1 and v2, and they're in some plane like this, and v3 is out of the plane. So I've got v3 there, v1 and v2. So first let's do the Gram-Schmidt process and find some orthonormal vectors describing this plane and its normal v3. So my first vector, e1, is going to be just the normalized version of v1. v1 here is of length root 3, 1 squared plus 1 squared plus 1 squared, all square rooted. So it's going to be 1 over root 3 times 1, 1, 1. That's a normalized version of v1. So then we can carry on, and I can find u2 is equal to v2 minus some number of e1s. So that's going to be, then the sum number is going to be the projection of v2 onto e1 times e1. So that's going to be 2, 0, 1 minus 2, 0, 1 dotted with e1, which is 1 over root 3, 1, 1, 1, times 1 over root 3, 1, 1, 1, because that's e1. So that's 201 minus, the root 3's are going to come outside, so I can just have them being a third. 201 dotted with 1, 1, 1 is 2 plus 0 plus 1 is 3. So that actually goes and has a party and becomes 1. And yeah, okay, I confess I fixed the example. So it's 201 minus 111, which is going to give me 1 minus 1, 1 minus 1 is 0. So 1 minus 1, 0. That's U2. Now if I want to normalize U2, I can say E2 is equal to the normalized version of U2, which is just 1 over root 2 times 1 minus 1, 0. So then I just need to find U3, and I can do the same again with U3. I can say that that's equal to V3 minus the projection of V3 onto E1 minus the projection of V3 onto E2. So that's going to be 3, 1 minus 1 minus 3, 1 minus 1 dotted with 1 over root 3, 1, 1, 1. And that's a number, and it's going in the direction of the unit vector of E2, of E1, minus V3 dotted with E2, so that's 3, 1 minus 1, dotted with 1 over root 2, 1 minus 1, 0, times E2, which is 1 over root 2, 1 minus 1, 0. So it's quite a complicated sum. So I've got an answer here, which I can do. 3, 1 minus 1 minus the 1 over root 3's come out again. 3 plus 1 minus 1 is 3, so that goes, and I've got 1, 1, 1 there, so that becomes 1, minus the halves are going to come out, the 1 over root 2's. I've got 3 minus 1 minus 0, so that's 2. So they cancel and become 1 again. As I say, I fixed the example to make my life easy. So then I've got 3, 1 minus 1 minus 1, 1, 1 minus 1 minus 1, 0. So therefore, I get an answer for U2 being 3 minus 1 minus 1, so that's 1. 1 minus 1 is 0, minus minus 1 is plus 1, minus 1 minus 1 is minus 2. And so I can then normalize that and get E3. So E3 is just the normalized version of that, which is going to be 1 over root 6 of 1, 1 minus 2. Now let's just check. So 1, 1 minus 2 is normal to 1, 1, 0. It is normal to 1, 1, 1. Those two are normal to each other, so our normal base is set. Just need to make sure that's 1 over root 6. They are all of unit length. So I can write down my new transformation matrix, which I'm going to call E. It's the transformation matrix described by the basis vectors E1, E2, E3. So I've got E1, E2, E3, all written down as column vectors. And that's going to be my transformation matrix that first contains the plane, notice, and then contains the normal to the plane. So I've redrawn everything just to get it all more compact so we can carry on. We've got our original two vectors V1 and V2, and we've defined E1 to be the normalized version of V1, and we've defined E2 to be the perpendicular part of V2 to E1, normalized to be of unit length. So these are all in a plane, and then E3 is normal to that plane. It's the bit of V3 that we can't make by projection onto V1 and V2, then of unit length. Now say I've got a vector R over here, R. Now what I want to do is reflect R down through this plane. So I'm going to drop R down through this plane. There he is when he intersects the plane. And then out the other side to get a vector R prime. And let's say that R has some number like, I don't know, 2, 3, 5. 2, 3, 5. Now, this is going to be really awkward. This plane's off at some funny angle composed of these vectors and even these basis vectors. It's at some funny angle, and then how do I drop it down and do the perpendicular? There's going to be a lot of trigonometry. But the neat thing here is that I can think of R as being composed of a vector that's in the plane, so some vector that's composed of E1s and E2s. So here's E1 here. And some vector that's normal, so some vector that's some number of E3s. And when I reflect it through, the bit that's in the plane is going to be the same, but this bit that's some number of E3s, this bit here, I'm just going to make into minus this bit here. So if I wrote that down as a transformation matrix, the transformation matrix in my basis E is going to be to keep the E1 bit the same, keep the E2 bit the same, so that's the E1 bit, that's the E2 bit, and then reflect the E3 bit from being up to being down, 0, 0, minus 1. So that's a reflection matrix in E3. So that's a reflection in the plane. So just by thinking about it quite carefully, I can think about what the reflection is. And that TE is in the basis of the plane, not in my basis, but in the basis of the plane. So that is easy to define. And therefore, if I can get the vector R defined in the plane's basis vector set, in the E basis, I can then do the reflection, and then I can put it back into my basis vector set, and then I have the complete transformation. So a way of thinking about that is that if I've got my vector R, and I'm trying to get it through some transformation matrix to R prime, but that's going to be hard. That's going to be tricky. But I can transform it into the basis of the plane. So I can make an R in the basis of the plane. And I'm going to do that using e to the minus 1. E to the minus 1 is the thing that got me into, got a vector of mine into Bare's basis, remember? Then I can do my transformation, I can do my reflection in the basis of the plane. I can do my reflection transformation. And then I will get R that's been transformed, primed, in the basis of the plane. Then I can read that back into my basis by doing E, because E is the thing that takes Bare's vector and puts it back into my basis. So if I go, I can avoid the hard thing by going around doing these three operations. So R, e to the minus 1, E inverse, T in the E basis, E. If I do those three things, I've done the complete transformation and I get R prime. So this problem reduces to doing that matrix multiplication. So we've got that, so we can just do the maths now, and then we'll be done. So I've just put the logic up there so that I can have the space down here for later, and I've put the transformation we're going to do there. A couple other things to note. One is, because E we've carefully constructed by our Gram-Schmidt process to be orthonormal, we know that E transpose is the inverse. So calculating the inverse here isn't going to be a pain in the neck. The other thing is, compared to the situation with Bare where we're changing bases, here we're changing from our vector R to Bare's, or actually the plane's coordinate system. Then we're doing the transformation of the reflection in the plane, and then we're coming back to our basis. So the E and the e to the minus 1 are flipped compared to the last video because we're doing the logic the other way around. It's quite neat, right? The actual multiplication of doing this isn't awfully edifying. It doesn't build you up very much. It's just doing some arithmetic. So I'm going to write it down here, and if you want to verify it, you can pause the video, and then we'll come back and we'll comment on it. So this is TE times the transpose of E. Then I take that and multiply it by E itself, and I get E, TE, E transpose, which is this guy, simplifies to this guy, so that's T. All comes out quite nicely. So that's very, very nice. So then we can apply that to R, so we can say that T times R is equal to T times our vector 2, 3, 5. and that's going to give us r prime, and that gives us an answer of 1/3 of 11, 14, 5. So r prime here is equal to 1/3 of 11, 14, and 5. So that's a process that would have been very, very difficult to do with trigonometry, but actually with transformations, once we get into the plane of the mirror and the normal to the mirror, then it all becomes very easy to do that reflection operation. And it's quite magical, really. It's really amazing. So that's really nice, right? It's really cool. So what we've done here is we've done an example where we've put everything we've learned about matrices and vectors together to describe how to do something fun like reflect a point in space in a mirror. This might be useful, for instance, if you want to transform images of faces for the purposes of doing facial recognition. You know, transform my face from being like that to being like that. And then we could use our neural networks, our machine learning, to do that facial recognition part. In summary, this week we've gone out into the world with matrices and learned about constructing orthogonal bases, changing bases, and we've related that back to vectors and projections. So it's been a lot of fun. And it sets us up for the next topic, which Sam is going to lead on eigenvalues and eigenvectors.
Welcome to Module 5 of the Linear Algebra course. I'm Sam, and I'll be taking over from David for this final topic. We're going to be focusing on eigenproblems, which will require us to draw on nearly all of the ideas that you've learned in the previous 4 modules. Finally, we'll be applying this new tool to recreate Google's famous method for taking internet search results and ordering them by relevance, known as the Pagerank algorithm. I hope you enjoy this module and make use of the forums to let us know how you're getting on. The word eigen is perhaps most usefully translated from the German as meaning characteristic. So when we talk about an eigen problem, we're talking about finding the characteristic properties of something. But characteristic of what? This module, like the previous weeks, will try and explain this concept of eigenness primarily through a geometric interpretation, which allows us to discuss images rather than immediately getting tangled up in the maths. When I first learnt this topic, not only did we start by grinding through formulae, we also spent very little time discussing what all the maths was doing. This topic is often considered by students to be quite tricky, but it's my belief that once you know how to sketch these problems, the rest is just algebra. So, as you've seen from previous weeks, it's possible to express the concept of linear transformations using matrices. These operations can include scalings, rotations, and shears. Often, when applying these transformations, we are thinking about what they might do to a specific vector. However, it can also be useful to think about what it might look like when they're applied to every vector in the space. This can be most easily visualized by drawing a square centered at the origin, and then seeing how your shape is distorted when you apply the transformation. So if we apply a scaling of 2 in the vertical direction, the square would now become a rectangle. Whereas if we applied a horizontal shear to the space, it might look something like this. Now, here's the key concept. We are using our little square to help us visualize what is happening to many vectors. But notice that some vectors end up lying along the same line that they started on, whereas others do not. To highlight this, I'm going to draw 3 specific vectors onto our initial square. Now, let's consider our vertical scaling again and think about what will happen to these 3 vectors. As you can see, the horizontal green vector is unchanged, pointing in the same direction and having the same length. The vertical pink vector is also still pointing in the same direction as before, but its length has doubled. Lastly, the diagonal orange vector used to be exactly 45 degrees to the axis. Its angle has now increased, as has its length. I hope you can see that actually, besides the horizontal and vertical vectors, any other vector's direction would have been changed by this vertical scaling. So in some sense, the horizontal and vertical vectors are special. They are characteristic of this particular transform, which is why we refer to them as eigenvectors. Furthermore, because the horizontal vector's length was unchanged, we say that it has a corresponding eigenvalue of 1, whereas the vertical eigenvector doubled in length, so we say it has an eigenvalue of 2. So, from a conceptual perspective, That's about it for 2D eigenproblems. We simply take a transform and we look for the vectors who are still laying along the same span as before. And then we measure how much their length has changed. This is basically what eigenvectors and their corresponding eigenvalues are. Let's look at two more classic examples to make sure that we can generalize what we've learned. Here's our marked up square again. And now let's look at pure shear, where pure means that we aren't performing any scaling or rotation in addition, so the area is unchanged. As I hope you spotted, it's only the green horizontal line that is still laying along its original span, and all the other vectors will be shifted. Finally, let's look at rotation. Clearly, this thing has got no eigenvectors at all, as all of the vectors have been rotated off their original span. In this lecture, we've already covered almost all of what you need to know about eigenvectors and eigenvalues. Although we've only been working in 2 dimensions so far, the concept is exactly the same in 3 or more dimensions. In the rest of the module, we will be having a look at some special cases, as well as discussing how to describe what we've observed in more mathematical terms. As we saw previously, eigenvectors are those which lie along the same span both before and after applying a linear transform to a space. And then eigenvalues are simply a amount that each of those vectors has been stretched in the process. In this video, we're going to look at 3 special cases to make sure the intuition we've built so far is robust, and then we're going to try and extend this concept into 3 dimensions. The first example we're going to consider is that of a uniform scaling, which is where we scale by the same amount in each direction. As you will hopefully have spotted, not only are all 3 of the vectors that I've highlighted eigenvectors, but in fact, for a uniform scaling, any vector would be an eigenvector. In this second example, we're going to look at rotation. In the previous video, we applied a small rotation, and we found that it had no eigenvectors. However, there is one case of non-zero pure rotation which does have at least some eigenvectors, and that is 180 degrees. As you can see, the 3 eigenvectors are still laying on the same spans as before, but just pointing in the opposite direction. This means that once again, all vectors for this transform are eigenvectors, and they all have eigenvalues of -1, which means that although the eigenvectors haven't changed length, they are all now pointing in the opposite direction. This third case, we're going to look at a combination of a horizontal shear and a vertical scaling, and it's slightly less obvious than some of the previous examples. Just like the pure shear case we saw previously, the green horizontal vector is an eigenvector, and its eigenvalue is still 1. However, despite the fact that neither of the 2 vectors shown are eigen, this transformation does have 2 eigenvectors. Here, I've now added the second eigenvector onto the image, and it shows us that although the concept is fairly straightforward, eigenvectors aren't always easy to spot. Let's now apply the inverse transform and watch our parallelogram go back to its original square, but this time with our eigenvector visible. Hopefully, you're at least convinced that it is indeed an eigenvector, and as it stays on its own span. This problem is even tougher in 3 or more dimensions, and many of the uses of eigentheory in machine learning frame the system as being composed of hundreds of dimensions or more. So clearly, we're going to need a more robust mathematical description of this concept to allow us to proceed. Before we do, let's just take a look at one quick example in 3D. Clearly, scaling and shear are all going to operate in much the same in 3D as they do in 2D. However, rotation does take on a neat new meaning. As you can see from the image, although both the pink and green vectors have changed direction, the orange vector has not moved. This means that the orange vector is an eigenvector, but it also tells us, as a physical interpretation, that if we find the eigenvector of a 3D rotation, it means we've also found the axis of rotation. In this video, we've covered a range of special cases, which I hope have prompted the questions in your mind about how we're going to go about writing a formal definition of an eigenproblem. And this is exactly what we're going to be discussing next time. See you then. Hopefully, you all now have a reasonable feeling for what an eigenproblem looks like geometrically. So in this video, we're going to formalize this concept into an algebraic expression, which will allow us to calculate eigenvalues and eigenvectors whenever they exist. Once you've understood this method, we'll be in a good position to see why you should be glad that computers can do this for you. If we consider a transformation A, what we have seen is that if it has eigenvectors at all, then these are simply the vectors which stay on the same span following a transformation. They can change length and even point in an opposite direction entirely, but if they remain on the same span, they are eigenvectors. If we call our eigenvector x, then we can say the following expression. Ax equals lambda x. Where on the left-hand side, we're applying the transformation matrix A to a vector x. And on the right-hand side, we are simply stretching the vector x by some scalar factor lambda. So lambda is just some number. We're trying to find values of x that make the two sides equal. Another way of saying this is that for our eigenvectors, having A applied to them just scales their length, or does nothing at all, which is the same as scaling the length by a factor of 1. So in this equation, A is an n-dimensional transform, meaning it must be an n by n square matrix. The eigenvector x must therefore be an n-dimensional vector. To help us find the solutions to this expression, we can rewrite it by putting all the terms on one side and then factorizing. So, A minus lambda I times x equals 0. If you're wondering about where the I term came from, it's just an n by n identity matrix, which means it's a matrix the same size as A, but with 1s along the leading diagonal and 0s everywhere else. We didn't need this in the first expression we wrote, as multiplying vectors by scalars is defined. However, subtracting scalars from matrices is not defined, so that I just tidies up the maths without changing the meaning. Now that we have this expression, we can see that for the left-hand side to equal 0, either the contents of the brackets must be 0 or the vector x is 0. So we're actually not interested in the case where the vector x is 0. That's when it has no length or direction and is what we call a trivial solution. Instead, we must find when the term in the brackets is 0. Referring back to the material in the previous parts of the course, we can test if a matrix operation will result in a 0 output by calculating its determinant. So, det of A minus lambda I equals 0. Calculating the determinants manually is a lot of work for high-dimensional matrices. So let's just try applying this to an arbitrary 2 by 2 transformation. Let's say A equals A, B, C, D. Substituting this into our eigenfinding expression gives the following. Det of A, B, C, D minus lambda 0, 0, lambda. Evaluating this determinant, we get what is referred to as the characteristic polynomial, which looks like this. So, lambda squared minus A plus D lambda plus AD minus BC equals 0. Our eigenvalues are simply the solutions of this equation, and we can then plug these eigenvalues back into the original expression to calculate our eigenvectors. Rather than continuing with our generalized form, this is a good moment to apply this to a simple transformation for which we already know the eigensolution. Let's take the case of a vertical scaling by a factor of 2, which is represented by the transformation matrix A equals 1, 0, 0, 2. We can then apply the method that we just described and take the determinant of A minus lambda I and then set it to 0 and solve. So, the determinant of 1 minus lambda, 0, 0, 2 minus lambda equals 1 minus lambda, 2 minus lambda, which is of course equal to 0. This means that our equation must have solutions at lambda equals 1 and lambda equals 2. Thinking back to our original eigenfinding formula, a minus lambda I x equals 0, we can now sub these two solutions back in. So thinking about the case where lambda equals 1, we can say 1 minus 1, 0, 0, 2 minus 1 times this x vector, x1 and x2, must equal to 0, 0, 0, 1 times x1, x2. Therefore, we've got 0 and x2 must equal 0. Now thinking about the case where lambda equals 2, at lambda equals 2, you get 1 minus 2 and 2 minus 2. And then you get, of course, minus 1, 0, 0, 0, which equals 2 minus x1, 0, which equals 0. So what do these two expressions tell us? Well, in the case where our eigenvalue lambda equals 1, we've got an eigenvector where the x2 term must be 0. But we don't really know anything about the x1 term. Well, this is because, of course, any vector that points along the horizontal axis could be an eigenvector of this system. So we write that by saying at lambda equals 1, x, our eigenvector, can equal anything along the horizontal axis as long as it's 0 in the vertical direction. So we put in an arbitrary parameter, t. Similarly, for the lambda equals 2 case, we can say that our eigenvector must equal 0t, because as long as it doesn't move at all in the horizontal direction, any vector that's purely vertical would therefore also be an eigenvector of this system, as they all would lie along the same span. So now we have two eigenvalues and their two corresponding eigenvectors. Let's now try the case of a rotation by 90 degrees anti-clockwise to ensure that we get the result that we expect, which, if you remember, is no eigenvectors at all. The transformation matrix corresponding to a 90-degree rotation is as follows. A equals 0, minus 1, 1, 0. So, applying the formula once again, we get the determinant of 0 minus lambda minus 1, 1, 0 minus lambda, which, if we calculate this through, comes out to lambda squared plus 1 equals 0, which doesn't have any real numbered solutions at all, hence no real eigenvectors. We could still calculate some complex eigenvectors using imaginary numbers, but this is beyond what we need for this particular course. Despite all the fun that we've just been having, the truth is that you will almost certainly never have to perform this calculation by hand. Furthermore, we saw that our approach required finding the roots of a polynomial of order n, i.e. the dimension of your matrix, which means that the problem will very quickly stop being possible by analytical methods alone. So when a computer finds the eigensolutions of a 100-dimensional problem, it's forced to employ iterative numerical methods. However, I can assure you that developing a strong conceptual understanding of eigenproblems will be much more useful than being really good at calculating them by hand. In this video, we translated our geometrical understanding of eigenvectors into a robust mathematical expression and validated it on a few test cases. But I hope that I've also convinced you that working through lots of eigenproblems, as is often done in engineering undergraduate degrees, is not a good investment of your time if you already understand the underlying concepts. This is what computers are for. Next video, we'll be referring back to the concept of basis change to see what magic happens when you use eigenvectors as your basis. See you then. So now that we know what eigenvectors are and how to calculate them, we can combine this idea with the concept of changing basis, which was covered earlier in the course. What emerges from this synthesis is a particularly powerful tool for performing efficient matrix operations called diagonalization. Sometimes we need to apply the same matrix multiplication many times. For example, imagine that a transformation matrix T represents the change in location of a particle after a single time step. So we can write that our initial position, described by vector v0, multiplied by the transformation t, gives us our new location v1. To work out where our particle will be after 2 time steps, we can find v2 by simply multiplying v1 by t, which is of course the same thing as multiplying v0 by t 2 times. So, v2 equals t squared times v0. Now, imagine that we expect this same linear transformation to occur every time step for n time steps, where we can write vn is t to the power of n times v0. You've already seen how much work it takes to apply a single 3D matrix multiplication. So if we were to imagine that t tells us what happens in 1 second, but we'd like to know where our particle is in 2 weeks from now, then n is going to be around 1.2 million, i.e., we'd need to multiply t by itself more than 1 million times, which may take quite a while. If all the terms in the matrix are 0, except for those along the leading diagonal, we refer to it as a diagonal matrix. And when raising matrices to powers, diagonal matrices make things a lot easier. In fact, have a go just now to see what I mean. All you need to do is put each of the terms on the diagonal to the power of n, and you've got the answer. So, in this case, t to the n is a to the n, b to the n, and c to the n. It's simple enough. But what if t is not a diagonal matrix? Well, as you may have guessed, the answer comes from eigenanalysis. Essentially, what we're going to do is simply change to a basis where our transformation t becomes diagonal, which is what we call an eigenbasis. We can then easily apply our power of n to the diagonalized form and finally transform the resulting matrix back again, giving us t to the power of n, but avoiding much of the work. As we saw in the section on changing basis, each column of our transform matrix simply represents the new location of the transformed unit vectors. So, to build our eigenbasis conversion matrix, we just plug in each of our eigenvectors as columns. C equals eigenvector 1, eigenvector 2, and eigenvector 3, in this case, as we're using a 3-dimensional example. However, don't forget that some of these may be complex, so not easy to spot using the purely geometrical approach, but they appear in the maths just like the others. Applying this transform, we find ourselves in a world where multiplying by t is effectively just a pure scaling, which is another way of saying that it can now be represented by a diagonal matrix. Crucially, this diagonal matrix, D, contains the corresponding eigenvalues of the matrix T. So D equals lambda 1, lambda 2, and lambda 3, with zeros elsewhere. We're so close now to unleashing the power of eigen. The final link that we need to see is the following. Bringing together everything we've just said, it should now be clear that applying the transformation T is just the same as converting to our eigenbasis, applying the diagonalized matrix, and then converting back again. So T equals C D C inverse, which suggests that T squared can be written as C D C inverse multiplied again by C D C inverse. So hopefully you've spotted that in the middle of our expression, on the right-hand side, you've got C multiplied by C inverse. But multiplying a matrix and then by its inverse is just the same as doing nothing at all. So we can simply remove this operation. Equals C d c inverse. And then we can finish this expression by saying, well, this must be c d squared c inverse. We can, of course, then generalize this to any power of t we'd like. So finally, we can say that t to the power of n is going to equal c d to the power of n multiplied by c inverse. We now have a method which lets us apply a transformation matrix as many times as we'd like without paying a large computational cost. This result brings together many of the ideas that we've encountered so far in this course. And in the next video, we'll work through a short example just to ensure that this approach lines up with our expectations when applied to a simple case. See you then. Now that we've walked through the theory of eigenbases and diagonalization, let's have a go at a simple 2D example where we can see the answer graphically, so we'll know whether or not our method has worked as expected. Consider the transformation matrix T equals 1, 1, 0, 2. Hopefully, you'd feel fairly comfortable at this point in drawing the transformed square and vectors that we used in the previous examples. As the first column is just 1, 0, this means that our I hat vector will be unchanged. However, the second column tells us that j hat, the second vector, will be moving to the point 1, 2. Let's also consider the orange diagonal vector to point 1, 1. Multiplying through gives us 1, 1, 0, 2 multiplied by 1, 1. So thinking about rows times cols, we're going to get 1 plus 1 and 0 plus 2, which gives us 2, 2. It's interesting to consider that this particular transform could be decomposed into a vertical scaling by a factor of 2, and then a horizontal shear by a half step. Because we've chosen such a simple transformation, hopefully you've already spotted the eigenvectors and can state their eigenvalues. These are, at lambda equals 1, our eigenvector is 1, 0, and at lambda equals 2, our eigenvector equals 1, 1. Now let's consider what happens to the vector minus 1, 1 when we apply t. So, 1, 1, 0, 2 applied to minus 1, 1. This time is going to equal rows times cols, minus 1 plus 1, and 0 plus 2, which equals 0, 2. And if we apply t again, we're going to get the following. 1, 1, 0, 2 applied to 0, 2, which is going to equal rows times cols again, 0 plus 2, and 0 plus 4. So this thing finally is going to equal 2, 4. Now instead, if we were to start by finding t squared, so t squared is going to equal this matrix multiplied by itself. So applying rows times cols, we're going to get 1 times 1 times 1 times 0, so that's 1. Rows times cols here, we're going to get a 3. Rows times cols here, we're going to get a 0. Rows times cols here, we're going to get a 4. Now we can apply this to our vector and see if we get the same result. So 1, 3, 0, 4 multiplied by minus 1, 1 is going to equal rows times cols, so we're going to get minus 1 plus 3 and 0 plus 4, which of course equals 2, 4. We can now try this whole process again, but using our eigenbasis approach. We've already built our conversion matrix C from our eigenvectors. So C is going to equal 1, 0, 1, 1. But we're now going to have to find its inverse. However, because we've picked such a simple 2x2 example, it's possible just to write this inverse down directly by considering that C would just be a horizontal shear one step to the right. So C inverse must just be this same shift back to the left again. So C inverse is going to equal 1 minus 1, 0, 1. It's worth noting that despite how easy this was, I would still always feed this to the computer instead of risking making silly mistakes. We can now construct our problem. So t squared is going to equal c d squared c inverse, which of course in our case is going to equal 1, 1, 0, 1, multiplied by our diagonal matrix, which is going to be 1 and 2, and that's all squared, multiplied by c inverse, which is 1 minus 1, 0, 1. Working this through, we can see that, let's keep this first matrix, 1, 1, 0, 1, and work out this bit. So we'll say, okay, this is going to be 1 and 4 on the diagonal, 1 minus 1, 0, 1. And let's work out these two matrices here. So we've got 1, 1, 0, 1 multiplied by, so we're doing rows times columns in each case. So for example, 1, 0 times 1, 0, we get a 1 here. We're going to do the second row in the first column, we get a 0 there. First row and second column, we're going to get a minus 1 there. And the second row and the second column, we're going to get a 4 here. Okay, and then working it through one more step, we're going to see that we get more grinding. We get first row, first column, 1. Second row, first column, 0. First row, second column is 3. And second row, second column is 4. And applying this to the vector minus 1, 1, we're going to get something like this. So 1, 3, 0, 4 applied to minus 1, 1 is going to be rows times cols. So minus 1 plus 3 and 0 plus 4, which equals 2, 4, which pleasingly enough is the same result as we found before. Now, there is a sense in which, for much of mathematics, once you're sure that you've really understood a concept, then because of computers, you may never have to do this again by hand. However, it is still good to work through a couple of examples on your own, just to be absolutely sure that you get it. There are of course many aspects of eigentheory that we haven't covered in this short video series, including undiagonizable matrices and complex eigenvectors. However, if you are comfortable with the core topics that we've discussed, then you're already in great shape. In the next video, we're going to be looking at a real-world application of eigentheory to finish off this linear algebra course. This is a particularly famous application which requires abstraction away from the sort of geometric interpretations that we've been using so far, which means that you'll be taking the plunge and just trusting the maths. See you then. The final topic of this module on eigenproblems, as well as the final topic of this course as a whole, will focus on an algorithm called Pagerank. This algorithm was famously published by and named after Google founder Larry Page and colleagues in 1998, and was used by Google to help them decide which order to display their websites when they returned from search. The central assumption underpinning Pagerank is that the importance of a website is related to its links to and from other websites. And somehow, eigentheory comes up. This bubble diagram represents a model mini-internet, where each bubble is a web page, and each arrow from A, B, C, and D represents a link on that web page which takes you to one of the others. We're trying to build an expression that tells us, based on this network structure, which of these web pages is most relevant to the person who made the search. As such, we're going to use the concept of procrastinating Pat, who is an imaginary person who goes on the internet and just randomly clicks links to avoid doing their work. By mapping all the possible links, we can build a model to estimate the amount of time we would expect Pat to spend on each web page. We can describe the links present on page A as a vector, where each row is either a 1 or a 0 based on whether there is a link to the corresponding page, and then normalize the vector by the total number of links, such that they can be used to describe a probability for that page. For example, the vector of links from page A would be 0, 1, 1, 1, because vector A has links to sites B, to C, and to D, but it doesn't have a link to itself. Also, because there are 3 links on this page in total, we would normalize by a factor of a third, so that the total click probability sums to 1. So we can write LA equals 0, a third, a third, a third. Following the same logic, the link vectors of the next 2 sites are shown here. And finally, for page D, we can write LD is going to equal, so D is connected to B and C, but not A, 2 sites in total, 0, a half, 0. We can now build our link matrix L by using each of our link vectors as a column, which you can see will form a square matrix. What we're trying to represent here with our matrix L is the probability of ending up on each of the pages. For example, the only way to get to A is by being at B. So you then need to know the probability of being at B, which you could have got to from either A or D. As you can see, this problem is self-referential, as the ranks of all the pages depend on all the others. Although we built our matrix from columns of outward links, we can see that the rows describe inward links normalized with respect to their page of origin. We can now write an expression which summarizes the approach. We're going to use the vector r to store the rank of all web pages. To calculate the rank of page A, you need to know 3 things about all other pages on the internet. What's your rank? Do you link to page A? And how many outgoing links do you have in total? The following expression combines these 3 pieces of information for web page A only. So, RA is going to equal the sum from j equals 1 to n, where n's all the web pages, of the link matrix relevant to web page A and location j multiplied by the rank at location j. So this is going to scroll through each of our web pages, which means that the rank of A is the sum of the ranks of all the pages which link to it, weighted by their specific link probability taken from matrix L. Now we want to be able to write this expression for all pages and solve them simultaneously. Thinking back to our linear algebra, we can rewrite the above expression applied to all web pages as a simple matrix multiplication. So R equals LR. Clearly, we start off not knowing R, so we simply assume that all the ranks are equally and normalize them by the total number of web pages in our analysis, which in this case is 4. So R equals a quarter, a quarter, a quarter, a quarter. Then, each time we multiply R by our matrix L, this gives us an updated value for R. So we can say that Ri plus 1 is going to be L times Ri. Applying this expression repeatedly means that we are solving this problem iteratively. Each time we do this, we update the values in R until eventually R stops changing. So now R really does equal LR. Thinking back to the previous videos of this module, this implies that R is now an eigenvector of matrix L, with an eigenvalue of 1. At this point, you might well be thinking, if we want to multiply R by L many times, perhaps this would be best tackled by applying the diagonalization method that we saw in the last video. But don't forget, this would require us to already know all the eigenvectors, which is what we're trying to find in the first place. So, now that we have an equation, and hopefully some idea of where it came from, we can ask our computer to iteratively apply it until it converges to find our rank vector. You can see that although it takes about 10 iterations for the numbers to settle down, the order is already established after the first iteration. However, this is just an artifact of our system being so tiny. So now we have our result, which says that as procrastinating Pat randomly clicks around our network, we would expect them to spend about 40% of their time on page D, but only about 12% of their time on page A, with 24% on each of pages B and C. We now have our ranking, with D at the top and A at the bottom and B and C equal in the middle. As it turns out, Although there are many approaches for efficiently calculating eigenvectors that have been developed over the years, repeatedly multiplying a randomly selected initial guess vector by your matrix, which is called the power method, is still very effective for the PageRank problem for two reasons. Firstly, although the power method will clearly only give you one eigenvector, when we know that there will be n for an n web page system, it turns out that because of the way we've structured our link matrix, the vector it gives you will always be the one that you're looking for, with an eigenvalue of 1. Secondly, although this is not true for the full web page mini-internet, when looking at the real internet, you can imagine that almost every entry in the link matrix will be 0, i.e., most pages don't connect to most other pages. This is referred to as a sparse matrix, and algorithms exist such that multiplication can be performed very efficiently. One key aspect of the PageRank algorithm that we haven't discussed so far is called the damping factor, d. This adds an additional term to our iterative formula. So r, I plus 1, is now going to equal d times LRI plus 1 minus d over n. D is something between 0 and 1, and you can think of it as 1 minus the probability with which procrastinating Pat suddenly randomly types in a web address rather than clicking on a link on his current page. The effect that this has on the actual calculation is about finding a compromise between speed and stability of the iterative convergence process. There are over 1 billion websites on the internet today, compared with just a few million when the PageRank algorithm was first published in 1998. And so the methods for search and ranking have had to evolve to maximize efficiency, although the core concept has remained unchanged for many years. This brings us to the end of our introduction to the PageRank algorithm. There are, of course, many details which we didn't cover in this video, but I hope this has allowed you to come away with some insight and understanding into how the PageRank works, and hopefully the confidence to apply this to some larger networks yourself.
Hi there again. So that's it for this course on linear algebra in our little specialisation on mathematics for machine learning. Our goal here was to give you some of the underpinnings of linear algebra, vectors and matrices, in order to enable you to access neural networks, machine learning and data science courses more generally. By no means is this a course that a computer scientist or mathematician would be completely happy with as setting out the foundations required for more advanced work in linear algebra in a graduate course, say. Nor is it a comprehensive course on linear algebra. We simply haven't had the time, so there are many things left out that, in my own discipline, say, material science, I would consider quite fundamental. But we think it's more than enough for a social scientist, an engineer or a physicist to develop the understanding and insight required to access other courses on machine learning tools in order to do useful work to solve problems with machine learning in the real world. But still, we've done a lot of work here. We started out thinking about data and the sorts of problems we might have, primarily optimization problems like fitting parameters that model data, the distribution of height, and simultaneous equations like the apples and bananas price discovery problem. We've then used those to go on a journey exploring vector properties like linear combinations, vector addition and scalar multiplication. We've then gone on to find the modulus of a vector and the dot product and the related ideas of the scalar and vector projections. That's led us get into basis changes and vector transformations, which meant we had to define what we meant by a basis, by linear independence and the dimensionality of a vector space. We then got into matrices and how to do matrix operations and how to solve systems of simultaneous equations using algorithms. We then looked at basis transformations again using matrices and looked at how to construct a basis using the Gram-Schmidt approach. Sam then took us through eigenvectors and eigenvalues, how to find them, and then took us through how to construct Google's famous Pagerank algorithm. And through it all, you hopefully enjoyed using this knowledge and developing your understanding by trying the problems and exercises, which we hope has given you the confidence to say that you're really getting now on developing an intuitive understanding about all this stuff. So Sam and I and all of us on the team here at Imperial really hope you've enjoyed this course and that it's been valuable to you. Of course, this course is intended to link very closely to its companions on multivariate calculus and on machine learning, so we hope you'll check those out as well. And of course, whether you do that or not, we wish you the very best for the future, whatever your future endeavour.